The universe is everything we can observe and everything we can't. When cosmologists ask about the edge of the universe, they're not looking for a physical border or outer wall. They're trying to define the limits of what can be measured, detected, or influenced by light and gravity since the beginning of cosmic expansion. Over the past century, advances in astronomy and physics have transformed our understanding of these limits. Observations from ground-based telescopes, the Hubble Space Telescope, and now the James Webb Space Telescope have allowed scientists to measure how fast the universe is expanding, how its structure has evolved, and how far we can see in any direction. To grasp what this means, we first need to understand just how vast the universe really is. The infinite abyss. How big is the universe really? Outer space stretches in every direction, a seamless void so vast that human measurement becomes almost meaningless. When we look into the night sky, the light that reaches us is only a fraction of what truly exists. A thin slice of a universe that has no tangible edge, no physical wall, and no sign of stopping. Yet in science, we can still define what we call the observable universe, the portion of reality whose light has had time to reach us since the Big Bang. Astronomers estimate that this observable bubble has a diameter of roughly 93 billion light-years. That means, in any direction we look, the most distant galaxies we can detect are about 46.5 billion light-years away. Beyond that, the light from farther regions hasn't had enough time to travel across expanding space to reach our instruments. The edge we talk about, therefore, isn't a physical border, it's a limit of information. To understand how immense that is, imagine traveling at the speed of light, 300,000 kilometers per second. Even at that impossible pace, it would take 46.5 billion years to reach the visible limit in one direction. And by the time you arrived, the universe would have expanded further, placing your destination even farther away. This paradox illustrates the core truth of modern cosmology. The universe has no fixed edge, only horizons that shift as space itself stretches. Our perception of distance in the universe depends entirely on light. Every star, galaxy, and nebula sends photons racing through the vacuum, messengers that travel uninterrupted until they hit a telescope mirror or a detector. By analyzing their wavelengths, astronomers can measure how long that light has been in flight. The deeper we look, the older the light becomes. The farthest galaxies captured by the James Webb Space Telescope today emitted their glow when the universe was less than 400 million years old, just a fraction of its current 13.8 billion year age. These distant objects are not merely far away in space, they are far away in time. This creates a visual paradox. When we observe the universe, we are not seeing it as it is now, but as it once was. Every increase in distance is also a journey backward through the ages, toward the universe's earliest structures and first stars. The farther we push our telescopes, the closer we approach the faint, uniform background radiation that marks the ultimate boundary of sight, the cosmic microwave background, or CMB. Beyond that veil lies a universe we can only infer through mathematics, not observation. One of the most common misconceptions about the universe is that it's expanding outward from a single point, as if the Big Bang were an explosion scattering galaxies into pre-existing space. The reality is more subtle and stranger. The Big Bang did not happen in space, it created space itself. Every point in the universe was once compressed into an incredibly dense, hot state. As it expanded, space stretched uniformly in all directions. There is no center and no edge, only expansion occurring everywhere at once. To visualize this, cosmologists often use the example of raisin bread dough. As it rises, the dough expands evenly, and every raisin moves away from every other raisin. From the perspective of any one raisin, it appears as though everything is receding. But there is no single center of that motion within the dough itself. That's how galaxies behave in our universe. Every galaxy observes others moving away, and the farther apart they are, the faster they recede. This linear relationship, known as Hubble's law, is one of the foundational discoveries of modern astronomy. In the early 20th century, astronomer Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to study faint patches of light, then called spiral nebulae. By analyzing the light from these objects, he found they were made of stars, entire galaxies beyond our own Milky Way. But more striking was his measurement of their redshift, the stretching of light toward longer wavelengths as the galaxies moved away from Earth. Hubble discovered that nearly all distant galaxies exhibited this redshift, and that the amount of stretching increased with distance. This meant that space itself was expanding, carrying galaxies with it like dots on a stretching rubber sheet. The farther away a galaxy is, the faster it appears to recede. Hubble's observation shattered the static universe model and confirmed that the cosmos had a dynamic history, one that began with a single moment of origin. If we were to compress the entire observable universe into a model 1 meter across, the solar system would be invisible. Even the Milky Way would shrink to less than a grain of dust. Our galaxy contains roughly 100 billion stars and stretches about 100,000 light-years across. The Andromeda galaxy, our nearest large neighbor, lies 2.5 million light-years away. But the observable universe holds an estimated 2 trillion galaxies, each with billions of stars, planets, and potentially habitable worlds. Between these galaxies lie enormous stretches of near-empty space, cosmic voids spanning hundreds of millions of light-years. These voids form part of a vast structure called the cosmic web, where galaxies are arranged along filaments and clusters that resemble a three-dimensional network. When scientists map this web using redshift surveys, they find a universe without symmetry or boundaries, yet governed by the same physical laws everywhere. Whether we observe galaxies 10 million or 10 billion light-years away, their basic composition, hydrogen, helium, gravity, and light, remains the same. This uniformity is one of cosmology's great mysteries. It suggests that, despite its infinite scale, the universe was once small enough for its matter and energy to mix evenly before expanding beyond contact. The observable universe might seem like a complete picture, but it represents only a fragment of the whole. Because space expands faster than light can travel across it, regions beyond a certain distance are forever unreachable. Light emitted from those regions will never reach us, not even if we wait forever. This limit defines what cosmologists call the cosmic event horizon. It's the true edge of what can ever influence us, not a wall, but a limit of causality. Currently, that horizon lies roughly 16 billion light-years away in any direction. Beyond it, galaxies still exist and move, but their light will never arrive. They are permanently beyond communication. What's remarkable is that this horizon is growing even as the universe expands. Over time, galaxies that are visible today will slip beyond it, vanishing from our view forever. Billions of years from now, future astronomers may see only a dim, isolated Milky Way, surrounded by darkness. The universe has no edge in the ordinary sense, but it may have curvature, the way a surface can bend through higher dimensions. If the cosmos is closed, it could theoretically loop back on itself, much like the surface of a sphere. Traveling far enough in one direction would eventually bring you back to your starting point. However, observations from the Planck satellite and other missions suggest that on large scales, space is remarkably flat, meaning parallel lines remain parallel, and geometry follows Euclidean rules across billions of light-years. Flatness implies that the universe is either infinite or so vast that any curvature is undetectable within our observable range. It also indicates that the total density of matter and energy is precisely balanced with the critical value that determines cosmic geometry. This perfect balance is another puzzle. If the universe had been even slightly more or less dense in its early moments, it would have either collapsed long ago or expanded too rapidly for galaxies to form. Our understanding of the universe's size is constantly evolving. Each new generation of telescopes extends our reach a little farther, not by traveling through space, but by capturing older light from deeper time. The James Webb Space Telescope, operating from its stable orbit around the Sun, has already pushed the visible boundary closer to the dawn of creation. Future missions, like the Nancy Grace Roman Space Telescope, will map billions of galaxies and refine our measurements of cosmic expansion. Yet, no matter how advanced our instruments become, the ultimate limit remains, the point beyond which light has never reached us and never will dot. That invisible frontier defines what we can know. Beyond it lies a universe still expanding, perhaps infinite, perhaps curved upon itself, but forever beyond direct observation. And that leads to our next mystery. If the universe is expanding, what exactly is driving that expansion, and how far can it go? The observable universe, our cosmic bubble. When cosmologists talk about the observable universe, they're referring to a very specific concept: the region of space from which light has had time to reach us since the Big Bang. This forms a sphere centered on Earth, not because Earth is special, but because we're the observers. An alien civilization in a distant galaxy would see their own observable universe, centered on them, largely overlapping with ours, but extending in different directions. The radius of this observable sphere is approximately 46.5 billion light-years. This number comes from detailed calculations involving the expansion history of the universe. Light from the most distant observable objects was emitted when the universe was very young, and those objects were much closer to us. But during the billions of years the light has been traveling, space has been expanding, carrying those objects farther away. By the time the light reaches us, the objects that emitted it are now 46.5 billion light-years distant. This creates an apparent paradox. If the universe is 13.8 billion years old, how can we see objects 46.5 billion light-years away? The answer lies in the expansion of space. The light didn't have to travel 46.5 billion light-years through static space. It traveled through expanding space, and the stretching of space during the journey allowed it to cover more ground than the speed of light multiplied by the age of the universe would suggest. Let's make this concrete with an example. Consider a galaxy that emitted light 13 billion years ago, when the universe was just 800 million years old. At that time, the galaxy was perhaps 4 billion light-years from the spot that would eventually become Earth. The light began its journey toward us, but space was expanding, stretching the distance between us and the galaxy, even as the light traveled. By the time the light reaches us today, that galaxy is now roughly 30 billion light-years away. We see the galaxy as it was 13 billion years ago, but it's now much farther from us than when the light was emitted. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The total number of stars in the observable universe is approximately 10 to the power of 24, a trillion. This staggering number represents only what we can observe. Beyond our cosmic horizon, there may be vastly more galaxies, stars, and planets that we will never see. The boundary of the observable universe is not sharp. It's not as if there's a wall at 46.5 billion light-years beyond which nothing exists. Rather, it's a horizon beyond which we simply cannot receive information. Light from beyond this horizon hasn't had time to reach us yet. As the universe ages, our observable universe grows. Light from more distant regions arrives, expanding our cosmic horizon. However, because the expansion of the universe is accelerating, driven by dark energy, the situation is more complex than simple linear growth. The edge of the observable universe is defined by the cosmic microwave background, CMB. This is the oldest light we can see, emitted when the universe was 380,000 years old. Before this time, the universe was opaque, a hot, dense plasma, where photons couldn't travel freely without scattering off electrons. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, photons could suddenly travel freely. This recombination event released a flood of light that has been traveling through space ever since, cooling and redshifting as the universe expands. Today, we detect this light as microwave radiation coming from all directions. The CMB forms a glowing shell around us at a distance of 46.5 billion light-years, the edge of the observable universe. We cannot see anything farther because before recombination, the universe was opaque. The CMB is our ultimate observational boundary for electromagnetic radiation. However, there are other ways to probe the early universe beyond the CMB. Neutrinos, which interact very weakly with matter, decoupled from the primordial plasma even earlier than photons, when the universe was about 1 second old. In principle, detecting this cosmic neutrino background would allow us to see earlier in the universe's history. Similarly, gravitational waves can propagate through the opaque early universe. Detecting primordial gravitational waves could provide information about the universe's first fractions of a second. The observable universe is not static. Every day, light from objects that were previously beyond our horizon arrives at Earth, expanding the volume of space we can observe. In principle, as the universe ages, we should be able to see more and more. However, the accelerating expansion complicates this. Dark energy is causing the expansion rate to increase over time. This means that distant galaxies are receding from us at ever faster rates. Eventually, a galaxy that is currently observable will recede so fast that its light can no longer reach us. The galaxy will cross our event horizon, disappearing from view forever. This creates a distinction between the particle horizon, the current edge of the observable universe, and the event horizon, the ultimate limit of what we will ever be able to observe. The particle horizon grows with time as light from more distant regions reaches us, but the event horizon marks the boundary beyond which objects are receding so fast due to accelerating expansion that their light will never reach us, even if we wait an infinite amount of time. Calculating the size of the observable universe requires knowledge of the universe's expansion history. This history is encoded in the Friedmann equations, derived from general relativity, which describe how the scale factor of the universe, a measure of its size, changes with time. The equations depend on the content of the universe: ordinary matter, dark matter, radiation, and dark energy. By measuring these components and their evolution, cosmologists can reconstruct the expansion history and determine the current size of the observable universe. Current measurements indicate that the universe is composed of approximately 5% ordinary matter, atoms, 27% dark matter, and 68% dark energy. Dark energy, characterized by negative pressure, drives the accelerating expansion. Ordinary and dark matter, on the other hand, exert gravitational attraction and would slow the expansion if they dominated. The balance between these components determines the fate of the observable universe. In the current era, dark energy dominates, and the expansion is accelerating. This means the observable universe is growing, but the rate at which new regions come into view is slowing. Eventually, in the far future, the observable universe will reach a maximum size. Galaxies beyond a certain distance will recede beyond our event horizon, and we will lose the ability to observe them. The universe will become increasingly empty from our perspective, with fewer and fewer galaxies visible. The expansion of space, not galaxies moving. One of the most common misconceptions about the universe's expansion is that galaxies are moving through space, like boats sailing across the ocean. This mental model, while intuitive, is fundamentally wrong. The expansion of the universe is not motion through space. It's the expansion of space itself. This distinction is crucial for understanding the edge of the universe. If galaxies were moving through a static pre-existing space, there would need to be a center to the expansion, a point from which all galaxies are receding. But observations show no such center. Every point in the universe sees galaxies receding in all directions, as if that point were the center. This is only possible if space itself is expanding uniformly. The concept comes from Einstein's general relativity, published in 1915. General relativity describes gravity not as a force, but as the curvature of spacetime. Mass and energy warp the fabric of spacetime, and objects move along the curved paths created by this warping. But general relativity also allows for spacetime itself to be dynamic. It can expand, contract, or oscillate. In 1922, Russian physicist Alexander Friedmann found solutions to Einstein's equations that described an expanding universe. Independently, Belgian priest and physicist Georges Lemaitre arrived at similar conclusions in 1927. These solutions suggested that the universe was not static, but evolving, either expanding or contracting. Einstein initially resisted this idea, even introducing a cosmological constant to his equations to force a static universe. He later called this his biggest blunder, after observations confirmed the universe's expansion. The observational evidence came from Edwin Hubble. In 1929, using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured the distances and velocities of galaxies. He found that more distant galaxies were receding faster, with velocities proportional to distance. This relationship, now called Hubble's law, is exactly what you'd expect from an expanding universe. If space is stretching uniformly, galaxies farther away have more space between us and them, so they recede faster. Hubble's law can be written simply as the recession velocity equals the Hubble constant multiplied by the distance, where v is the recession velocity, d is the distance, and the Hubble constant is the expansion rate of the universe. Current measurements put the Hubble constant at approximately 67 to 73 kilometers per second per megaparsec, though there's some tension between different measurement methods. This means that for every megaparsec, about 3.26 million light-years of distance, a galaxy recedes 67 to 73 kilometers per second faster. At large enough distances, this leads to recession velocities exceeding the speed of light. A galaxy 14 billion light-years away recedes at roughly the speed of light. Galaxies beyond this distance recede faster than light. This does not violate relativity because the galaxies are not moving through space faster than light. Space itself is expanding, carrying them along. There's no limit to how fast space can expand. This superluminal recession is key to understanding the edge of the observable universe. Light from galaxies receding faster than light can still reach us if they're within our particle horizon. Here's why. Imagine a photon emitted by a distant galaxy receding at twice the speed of light. Initially, the photon moves toward us at the speed of light, but space is carrying it away at twice the speed of light, so the net effect is that it's moving away from us. However, as the photon travels through space, it enters regions that are receding from us less rapidly. Eventually, it crosses into a region receding slower than the speed of light, at which point it makes progress toward us. Over billions of years, the photon can eventually arrive. This process only works up to a certain distance, though. Galaxies beyond the particle horizon are receding so fast that their light has not yet had time to cross into slower receding regions. And galaxies beyond the event horizon are in regions where space is expanding so fast that their light will never be able to overcome the expansion, no matter how long we wait. The expansion of space also explains the redshift of distant galaxies. As light travels through expanding space, its wavelength stretches along with space itself. Light that was originally blue or ultraviolet can be stretched into red or even infrared wavelengths by the time it reaches us. The farther the light travels, the more space expands during the journey and the greater the redshift. Cosmologists quantify redshift with the parameter redshift, defined as redshift equals the observed wavelength minus the emitted wavelength divided by the emitted wavelength, where wavelength is represented by lambda. A redshift of 1 means the wavelength has doubled. The universe has expanded by a factor of 2 since the light was emitted. The The most distant galaxies observed have redshifts of approximately 10 to 13, meaning the universe has expanded 11 to 14 times since that light was emitted. These galaxies are seen as they were just a few 100 million years after the Big Bang. The cosmic microwave background has a redshift of approximately 1100. The light we see as microwaves today was emitted as visible and ultraviolet light when the universe was 380,000 years old. Space has since expanded 1,100 times, stretching the wavelengths into the microwave part of the spectrum. Understanding that space itself expands is essential for grasping the nature of the universe's edge. The edge is not a boundary in space, it's a boundary of space-time. It's the limit of how far back in time and how far out in space we can observe. And because space-time is dynamic, this edge is constantly changing, shaped by the expansion rate and the universe's content. The cosmological horizon, a moving boundary. In a static universe, light from any object would eventually reach any observer given enough time. But the universe is not static, it's expanding. This creates cosmological horizons, boundaries beyond which objects cannot be observed either now or ever. There are three types of horizons in cosmology, each defining a different kind of edge. The particle horizon is the current edge of the observable universe. It represents the maximum distance from which light could have traveled to reach us since the Big Bang. The particle horizon's radius is about 46.5 billion light-years, as discussed earlier. This horizon grows with time as the universe ages and light from more distant regions arrives. The particle horizon is determined by integrating the speed of light over the entire history of the universe, accounting for the expansion of space. Mathematically, it's the comoving distance to the farthest point from which light emitted at the Big Bang could have reached us by now. The particle horizon defines the observable universe. Everything inside it can, in principle, be observed. Everything outside cannot yet be seen. The event horizon is more subtle and more disturbing. It's the boundary beyond which events happening now will never be observable to us, even if we wait an infinite amount of time. This horizon exists because the universe's expansion is accelerating. Galaxies beyond a certain distance are receding so fast that light emitted by them today will never reach us. The expansion of space will always outpace the light's progress toward us. The current event horizon is at a comoving distance of about 16 billion light-years. Objects beyond this distance are receding faster than light, and the acceleration of expansion ensures they will never cross back into the region from which light can reach us. As time passes, the event horizon actually shrinks in comoving coordinates. Galaxies that are currently just inside our event horizon will eventually cross it and disappear from view. In the far future, as dark energy continues to drive accelerating expansion, the observable universe will shrink. Distant galaxies will fade and redshift into invisibility as they cross our event horizon. Eventually, in trillions of years, only the galaxies in our local gravitationally bound group will remain visible. The rest of the universe will have receded beyond the horizon, leaving our descendants in an island universe, surrounded by darkness. The Hubble sphere is defined as the distance at which the recession velocity equals the speed of light. This is not a true horizon in the causal sense, but it's a useful concept. The Hubble radius is the speed of light divided by the Hubble constant, where the speed of light is c and the Hubble constant describes the universe's expansion rate. With the Hubble constant approximately 70 kilometers per second per megaparsec, the Hubble radius is about 14 billion light-years. Galaxies outside the Hubble sphere are receding faster than light, but as explained earlier, their light can still reach us if they're inside the particle horizon. The Hubble sphere is not a barrier to observation. It's simply the distance at which recession velocity equals c. These horizons define different types of edges. The particle horizon is the edge of what we can currently see. The event horizon is the edge of what we will ever be able to see. And the Hubble sphere is the edge of the region where space is expanding slower than the speed of light. None of these horizons are physical barriers. You couldn't fly a spacecraft to them and bump into a wall. They're properties of space-time itself, defining limits of causal contact and information flow. If you traveled toward the edge of the observable universe, it would recede ahead of you. The horizon is observer-dependent. Every observer in the universe has their own set of horizons centered on their location. This observer dependence is a key feature of cosmological horizons. Unlike a black hole's event horizon, which is an absolute feature of spacetime, cosmological horizons depend on the observer's world line, their path through spacetime. Two observers at different locations, or with different velocities, will have different horizons. The existence of horizons means the universe is divided into causally disconnected regions. Events beyond our horizon cannot affect us, and we cannot affect them. In a very real sense, regions beyond the horizon are outside our universe, even though they're part of the same space-time. This leads to profound questions. If we can never observe or interact with regions beyond the horizon, do they even exist in a meaningful sense? Or is the observable universe all that meaningfully exists from our perspective? Most cosmologists take the view that regions beyond our horizon do exist. They're part of the same space-time fabric, governed by the same physical laws. The fact that we can't observe them is a limitation of our position in space-time, not a statement about whether they're real. An observer in one of those distant regions would see us beyond their horizon, yet we certainly exist. The cosmological horizon also has thermodynamic properties. In the 1970s, Stephen Hawking and others discovered that black hole event horizons have temperature and entropy. Similarly, cosmological horizons in an accelerating universe have a temperature, the de Sitter temperature, associated with them. This temperature is extraordinarily low, far colder than the cosmic microwave background, but it's non-zero in principle. The existence of this temperature suggests deep connections between gravity, quantum mechanics, and thermodynamics, connections that are still being explored. Measuring the universe, cosmic distance ladder. To understand the edge of the universe, we need to measure distances on cosmic scales. This is far from straightforward. We can't stretch a tape measure to distant galaxies, and direct parallax measurements work only for nearby stars. Cosmologists use a series of overlapping techniques called the cosmic distance ladder, each rung extending our reach farther into space. The first rung is parallax, the apparent shift in position of a nearby object when viewed from different locations. As Earth orbits the Sun, nearby stars appear to shift position relative to more distant background stars. By measuring this shift and knowing the diameter of Earth's orbit, we can triangulate the distance to stars up to a few hundred light-years away. The European Space Agency's Gaia satellite has measured parallaxes for over 1 billion stars, creating the most detailed 3D map of our galactic neighborhood. But parallax only works for relatively nearby objects. Beyond a few thousand light-years, the shifts become too small to measure accurately. However, to measure greater distances, astronomers use standard candles, objects with known intrinsic brightness. By comparing an object's intrinsic brightness with its apparent brightness, how bright it appears from Earth, we can calculate its distance using the inverse square law. Brightness decreases with the square of distance. Several types of standard candles exist. Cepheid variable stars pulsate with periods that correlate tightly with their intrinsic luminosity. By measuring a Cepheid's period, we know its true brightness and can calculate its distance. Cepheids are visible in nearby galaxies up to about 100 million light-years away, making them crucial for measuring distances within the local universe. Edwin Hubble used Cepheids in the Andromeda galaxy to prove that Andromeda was a separate galaxy, not a nebula within the Milky Way. This discovery expanded our conception of the universe enormously. The Hubble Space Telescope has since observed Cepheids in galaxies tens of millions of light-years away, establishing firm distance measurements that anchor the cosmic distance ladder. For greater distances, astronomers use type Ia supernovae. These stellar explosions occur when a white dwarf star accretes matter from a companion star until it exceeds a critical mass, about 1.4 solar masses, called the Chandrasekhar limit. The white dwarf undergoes runaway nuclear fusion, exploding with a luminosity that briefly outshines an entire galaxy. Because all type Ia supernovae involve white dwarfs exceeding the same mass limit, they explode with roughly the same intrinsic brightness, making them excellent standard candles. Type Ia supernovae are so bright they're visible across billions of light years. In the 1990s, two teams used distant supernovae to measure the expansion history of the universe. Their shocking discovery that the expansion is accelerating won the 2011 Nobel Prize in Physics. Dark energy, the mysterious component driving the acceleration, makes up 68% of the universe's energy density. For the most distant objects, cosmologists rely on redshift. As discussed, light from receding galaxies is stretched to longer, redder wavelengths by the expansion of space. The degree of redshift directly indicates how much the universe has expanded since the light was emitted. By measuring redshift and combining it with distance measurements from standard candles, cosmologists establish the relationship between redshift and distance. This allows them to estimate distances to objects too far away for standard candles to be useful. Galaxies with redshifts of 6 or higher, meaning the universe has expanded 7-fold since the light was emitted, are routinely observed by instruments like the James Webb Space Telescope. Another technique uses surface brightness fluctuations. In distant galaxies, individual stars blur together. But statistical analysis of the pixel-to-pixel variations in a galaxy's image can reveal information about its distance. This method works for elliptical galaxies and has been calibrated using Cepheids and other standard candles. For spiral galaxies, the Tully-Fisher relation links the galaxy's rotation speed, measured from Doppler shifts of gas, to its intrinsic luminosity. Faster rotating galaxies are more luminous. By measuring rotation and apparent brightness, we can estimate distance. A similar relation, the Faber-Jackson relation, applies to elliptical galaxies, linking the velocity dispersion of stars to luminosity. Massive objects bend spacetime, causing light to follow curved paths, gravitational lensing. When a massive galaxy or galaxy cluster lies between us and a more distant object, the intervening mass acts as a lens, distorting and magnifying the background object's image. By analyzing the geometry of the lensing, astronomers can estimate distances to both the lens and the lensed object. In the early universe, pressure waves, sound waves, propagated through the hot plasma before recombination. These waves left an imprint on the distribution of galaxies, a characteristic scale called the Baryon Acoustic Oscillation, BAO scale, about 500 million light-years. By surveying large numbers of galaxies and measuring the BAO scale, cosmologists can use it as a standard ruler to measure distances and the expansion rate of the universe. The CMB itself provides distance information. The pattern of hot and cold spots in the CMB has a characteristic angular scale determined by the physics of the early universe. By measuring this scale and comparing it to theoretical predictions, cosmologists constrain the geometry and expansion rate of the universe. Each of these techniques has uncertainties, and the cosmic distance ladder depends on careful calibration between rungs. Small errors at one rung propagate to higher rungs, so precision at every level is crucial. Currently, there's a tension between different measurements of the Hubble constant. Measurements using Cepheids and supernovae give the Hubble constant of approximately 73 km per second per megaparsec, while measurements from the cosmic microwave background give the Hubble constant of approximately 67 km per second per megaparsec. This discrepancy, called the Hubble tension, is one of the major unsolved problems in cosmology. It may indicate unknown systematics in the measurements, or it could point to new physics. Perhaps the properties of dark energy have changed over time, or there's an additional component of the universe we haven't accounted for. Resolving the Hubble tension is critical for understanding the universe's size, age, and fate. If the higher value is correct, the universe is expanding faster than we thought, meaning it's younger and the particle horizon is smaller. If the lower value is correct, our current models are broadly accurate. Either way, precise distance measurements are the foundation for understanding the edge of the universe. The cosmic microwave background echoes of the beginning. The cosmic microwave background is the oldest light in the universe and the ultimate edge of what we can observe with electromagnetic radiation. Detected in 1965 by Arno Penzias and Robert Wilson, earning them the Nobel Prize, the CMB is the afterglow of the Big Bang, a faint glow of microwave radiation coming from all directions. The CMB was emitted 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this recombination, the universe was a hot, opaque plasma. Photons scattered constantly off free electrons, unable to travel far without being absorbed or redirected. The universe was essentially foggy, like being inside a cloud. When recombination occurred, the fog cleared. Photons could suddenly travel freely through space without scattering. This first light has been traveling ever since, cooling and stretching as the universe expands. Originally emitted as visible and ultraviolet light at temperatures around 3000 Kelvin, it has redshifted into microwave wavelengths, corresponding to a temperature of 2.725 Kelvin today, just 2.725 degrees above absolute zero. The CMB is remarkably uniform. Measurements show that its temperature varies by only about 1 part in 100,000 across the sky. This uniformity tells us the early universe was extraordinarily homogeneous. But the tiny temperature fluctuations that do exist are incredibly important. They represent the seeds of all cosmic structure, the slight overdensities that eventually grew into galaxies, stars, and planets. The pattern of CMB fluctuations encodes vast amounts of information about the universe. The fluctuations are not random, but have a characteristic statistical pattern, with temperature variations on certain angular scales being more prominent. This pattern is determined by the physics of the early universe, how sound waves propagated through the plasma, how matter and radiation interacted, and the geometry of space. Two major space missions have mapped the CMB in exquisite detail. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, operating from 2001 to 2010, produced all-sky maps showing the temperature variations with unprecedented precision. The European Space Agency's Planck satellite, operating from 2009 to 2013, improved on WMAP's measurements, providing even finer resolution and more accurate data. Analysis of Planck data has given us precise values for key cosmological parameters. The universe is 13.787 plus or minus 0.020 billion years old. It consists of 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. The universe is spatially flat or very close to it, meaning its large-scale geometry is Euclidean. The Hubble constant, according to Planck, is 67.4 kilometers per second per megaparsec, though as mentioned, this conflicts with local measurements. The CMB also reveals the universe's homogeneity and isotropy on large scales. No matter which direction we look, the CMB has the same average temperature and the same statistical properties. This supports the Copernican principle. There's nothing special about our location in the universe. It looks roughly the same from anywhere. But the CMB does have one striking asymmetry, the dipole. When we account for our motion through space, we observe that the CMB is slightly hotter in one direction and cooler in the opposite direction. This is a Doppler shift caused by our motion relative to the CMB rest frame. The local group of galaxies, which includes the Milky Way and Andromeda, is moving at about 627 kilometers per second toward a region in the constellation Hydra. This motion is caused by the gravitational pull of mass concentrations in that direction, specifically the Shapley supercluster and other large structures. The CMB dipole defines a preferred frame of reference in cosmology, sometimes called the CMB rest frame. This is the frame in which the CMB appears isotropic, the same in all directions. While relativity says there's no absolute rest frame in the universe, the CMB rest frame is special because it's the frame in which the universe looks most symmetric. The surface of last scattering, the spherical shell from which the CMB photons were emitted, is the edge of the observable universe for electromagnetic radiation. We cannot see anything farther because before recombination, the universe was opaque. The CMB forms a cosmic photosphere, analogous to the Sun's photosphere, which marks the outer layer from which sunlight escapes. However, the universe existed before recombination. During the first 380,000 years, the universe went through extraordinary changes. It began in an incredibly hot, dense state at the Big Bang, then expanded and cooled. In the first second, particles and antiparticles annihilated, leaving a slight excess of matter that constitutes everything we see today. Nuclear reactions during the first few minutes synthesized light elements, hydrogen, helium, and traces of lithium. These primordial abundances match predictions from Big Bang nucleosynthesis, providing strong evidence for the hot Big Bang model. To probe earlier than the CMB, we need messengers other than photons. Neutrinos decoupled from the primordial plasma when the universe was about 1 second old, creating a cosmic neutrino background analogous to the CMB. This background has never been directly detected because the neutrinos are so cold and interact so weakly that current technology cannot capture them. But in principle, detecting the cosmic neutrino background would allow us to see farther back in time than the CMB. Gravitational waves offer another window into the early universe. Unlike electromagnetic radiation, gravitational waves can propagate through the opaque early universe without scattering. Primordial gravitational waves generated during the first fractions of a second by quantum fluctuations during inflation would carry information about the universe at energies and timescales far beyond what particle accelerators can reach. Detecting these waves, either directly with gravitational wave observatories or indirectly through their imprint on CMB polarization, would open an observational window to the universe's first moments. The CMB represents a fundamental observational limit. It's the wall beyond which electromagnetic astronomy cannot penetrate. This wall defines one kind of edge, not an edge of space, but an edge of observability. The universe beyond the CMB exists, governed by the same physics, but it's hidden behind the opaque veil of the pre-recombination plasma. To fully understand the universe's edge, we must accept that some edges are informational rather than spatial, boundaries of what we can know rather than boundaries of what exists. Dark energy, the force shaping the edge. Dark energy is the most mysterious component of the universe and the key to understanding its ultimate edge and fate. Discovered in 1998 through observations of distant type Ia supernovae, dark energy is a form of energy that permeates all of space and exerts negative pressure, driving the accelerating expansion of the universe. The discovery shocked the scientific community. For decades, cosmologists had assumed that gravity would slow the universe's expansion over time. The question was whether the universe had enough matter to eventually stop expanding and recollapse, a closed universe, or whether it would expand forever, gradually slowing but never stopping, an open universe. No one expected the expansion to be speeding up. Two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, reached the same conclusion. Distant supernovae were dimmer than expected, indicating they were farther away than predicted by models without dark energy. The universe's expansion rate was slower in the past and has been accelerating for the last several billion years. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Dark energy is characterized by its equation of state, Bu equals pressure divided by energy density, where pressure is P and energy density is Rho. For ordinary matter and dark matter, W is approximately 0, meaning they exert essentially no pressure. For radiation, W is 1/3. For dark energy, current observations suggest W is approximately -1, corresponding to a constant energy density even as the universe expands. This is the property of a cosmological constant, the term Einstein introduced and later abandoned. The cosmological constant, usually denoted by the Greek letter lambda, can be interpreted as energy inherent to space itself, vacuum energy. Even in the absence of matter and radiation, space possesses a baseline energy density. As the universe expands and the volume increases, the total dark energy increases proportionally. This is unlike matter and radiation, which dilute as space expands. The physics behind dark energy remains unknown. Quantum field theory predicts that the vacuum should have energy due to quantum fluctuations, with particles and antiparticles constantly popping in and out of existence. But when physicists calculate the expected vacuum energy density, they get a number that is 10 to the power of 120 times larger than observed. This is called the cosmological constant problem, and is arguably the worst prediction in the history of physics. Several alternative explanations for dark energy have been proposed. Quintessence models suggest dark energy is not constant but changes over time, driven by a dynamical scalar field. Modification of gravity theories propose that general relativity breaks down on cosmic scales, and what we interpret as dark energy is actually a sign that we need a new theory of gravity. Some models invoke extra dimensions or quantum effects of spacetime itself. Despite these alternatives, the simplest explanation that fits all current data is the cosmological constant, dark energy, with W equal to -1 and constant density. Future observations, particularly measurements of how the expansion rate changes with time, will constrain these models and potentially reveal the nature of dark energy. Dark energy's negative pressure has a repulsive gravitational effect. While ordinary gravity attracts, dark energy's anti-gravity pushes. As the universe expands and matter dilutes, dark energy comes to dominate. About 5 billion years ago, dark energy overtook matter as the dominant component of the universe's energy budget. Since then, expansion has been accelerating. This acceleration has profound implications for the universe's edge. In a matter-dominated universe without dark energy, the cosmological horizon would continue growing indefinitely. More and more distant regions would come into view as the universe aged. But in a dark energy-dominated universe, there's an ultimate limit to what we can ever observe: the event horizon. Galaxies currently beyond our event horizon, about 16 billion light-years in co-moving distance, will never be observable, no matter how long we wait. Light emitted by them today cannot overcome the accelerating expansion. As time passes, galaxies currently just inside our event horizon will cross it and fade from view. Their light will be stretched to infinite wavelengths, effectively becoming undetectable. In the far future, trillions of years from now, only gravitationally bound structures will remain visible. The local group of galaxies, including the Milky Way, Andromeda, and several dozen smaller galaxies, is bound together by gravity strongly enough to resist the expansion. These galaxies will eventually merge into a single giant elliptical galaxy, sometimes called Milkomeda. But everything beyond the local group will have receded beyond the event horizon. A civilization living in this far future would observe a universe that appears empty except for their own galaxy. The cosmic microwave background will have redshifted to such long wavelengths and low temperatures that it becomes undetectable. There will be no evidence of the Big Bang, no distant galaxies to observe, no expanding universe to measure. Such a civilization might conclude they live in a static, eternal universe containing a single galaxy surrounded by infinite empty space. Ironically, a view similar to what astronomers believed before Hubble's discoveries in the 1920s. This future scenario is called cosmic event horizon domination, or sometimes the Big Rip, though technically the Big Rip refers to a specific scenario where dark energy's density increases over time, eventually tearing apart bound structures. In the standard cosmological constant scenario, bound structures survive, but everything else disappears beyond the horizon. Dark energy also affects the ultimate fate of the universe. With dark energy dominating, the universe will expand forever, accelerating indefinitely. The expansion will continue to dilute matter and stretch apart structures. Stars will exhaust their fuel, galaxies will become dark, and eventually, in 10 to the power of 100 years or more, even black holes will evaporate through Hawking radiation. The universe will approach a state of maximum entropy, a cold, dark, diffuse soup of particles and radiation, still expanding forever. Understanding dark energy is crucial for determining whether the universe has an ultimate edge in time as well as space. If dark energy is truly constant, the universe has no end. It will expand forever. But if dark energy evolves, strengthening over time, it could lead to a big rip, where acceleration becomes so extreme that even atoms are torn apart. Alternatively, if dark energy weakens or reverses, the universe could stop expanding and begin contracting, leading to a big crunch. Current observations constrain dark energy to be very close to a cosmological constant, with W equal to -1.03, plus or minus 0.03. But the uncertainties leave room for scenarios where W evolves with time. Future missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission will measure dark energy's properties with unprecedented precision, potentially revealing whether the universe's ultimate edge is an eternal horizon or something else entirely. Inflation theory, the universe before the Big Bang. The Big Bang marks the beginning of the observable universe, but it's not necessarily the beginning of everything. Inflation theory, proposed in the early 1980s, suggests that the universe underwent a brief period of exponential expansion in its first fraction of a second, growing from subatomic scales to macroscopic size in less than 10 to the power of -32 seconds. This inflationary epoch preceded what we traditionally call the Big Bang, the hot, dense state from which the observable universe evolved. Inflation solves several problems that plagued the standard Big Bang model. The first is the horizon problem. The CMB is extraordinarily uniform, with temperature variations of only 1 part in 100,000. This uniformity suggests that different regions of the early universe were in thermal equilibrium. They had time to exchange energy and reach the same temperature. But according to the standard Big Bang model, regions of the universe separated by more than about 2 degrees on the sky could never have been in causal contact. They were too far apart for light to have traveled between them in the time since the Big Bang. How then did they reach the same temperature? Inflation solves this by proposing that before the hot Big Bang phase, the universe was much smaller and had time to reach equilibrium. Then inflation stretched this small, uniform region to enormous size, far larger than what we can observe today. Regions that are now on opposite sides of the observable universe were once close together in causal contact before inflation separated them. The second problem is the flatness problem. Observations show that the universe's geometry is extraordinarily flat. Its curvature is indistinguishable from zero. But a flat geometry is unstable in the standard Big Bang model. If the universe started with even a tiny amount of curvature, that curvature would grow rapidly over time. For the universe to be as flat as we observe today, it must have started with an almost perfectly flat geometry, fine-tuned to many decimal places. This seems contrived. Inflation solves the flatness problem by exponentially expanding space. Any initial curvature gets stretched out, much like how the surface of a balloon appears flatter as the balloon inflates. After sufficient inflation, even a highly curved space becomes effectively flat. Inflation naturally explains why the universe appears flat today without requiring fine-tuned initial conditions. The third problem is the monopole problem. Grand unified theories, which attempt to unify the electromagnetic weak and strong nuclear forces, predict the production of magnetic monopoles, particles with only one magnetic pole, north or south, rather than both. These monopoles should have been produced copiously in the early universe and should still be around today, but none have ever been detected. Inflation solves this by diluting monopoles. If monopoles were produced before inflation, the exponential expansion spread them out so thinly that we wouldn't expect to find any in the observable universe. Inflation is driven by a scalar field called the inflaton. This field has a potential energy curve, and during inflation, it sits in a high energy state, slowly rolling toward a lower energy. The energy of the inflaton field acts like dark energy, driving exponential expansion. When the inflaton reaches the bottom of its potential, it oscillates and decays, converting its energy into particles and radiation, the hot Big Bang. This process is called reheating. The details of the inflaton field and its potential are unknown. Many models exist, each with different predictions for how long inflation lasted, how much the universe expanded, and what patterns of density fluctuations were imprinted. But all inflationary models share key features: exponential expansion, a transition to the hot Big Bang phase, and the generation of quantum fluctuations that seed cosmic structure. Quantum fluctuations during inflation are crucial for understanding the edge of the observable universe. During inflation, quantum uncertainty causes the inflaton field to fluctuate slightly from point to point. These fluctuations are microscopic and random. But inflation stretches them to macroscopic scales, imprinting patterns of slight overdensities and underdensities in the universe. These patterns are the seeds that eventually grew into galaxies, galaxy clusters, and the large-scale structure of the universe. The quantum fluctuations also generate primordial gravitational waves, ripples in space-time itself. These gravitational waves would leave a distinctive signature in the polarization of the CMB, specifically a pattern called B-mode polarization. Detecting this signature would provide direct evidence for inflation and allow measurements of the energy scale at which inflation occurred. Several experiments have searched for inflationary gravitational waves. The BICEP 2 experiment claimed detection in 2014, but subsequent analysis showed the signal was contaminated by dust in our galaxy. The search continues with instruments like the BICEP Keck array, the South Pole Telescope, and the upcoming LightBird satellite. Detecting B-mode polarization would be one of the most significant discoveries in cosmology, confirming inflation and opening a window to physics at energies far beyond what particle accelerators can reach. Inflation has another profound implication. It suggests the universe is vastly larger than the observable region. If inflation occurred, the entire universe could be many orders of magnitude larger than what we can see, perhaps 10 to the power of 23 times larger or more, depending on how long inflation lasted. The observable universe would be a tiny bubble within a much larger cosmos, and the edge we observe is simply the limit of our observational horizon, not the edge of space itself. Some versions of inflation, called eternal inflation, propose that inflation never fully ends everywhere. While inflation stops in some regions, like ours, creating pocket universes or bubble universes with hot Big Bang phases, other regions continue inflating. This process creates an infinite multiverse, with countless pocket universes scattered through an eternally inflating background. Each pocket universe could have different physical properties, different fundamental constants, different particle physics, even different numbers of dimensions. Eternal inflation is controversial because it makes predictions that are difficult to test. If our observable universe is just one bubble in an infinite multiverse, we cannot observe other bubbles, they're beyond our horizon. And we cannot verify the multiverse's existence directly. However, collisions between bubbles could potentially leave observable signatures in the CMB, and statistical arguments about where we should expect to find ourselves in such a multiverse, anthropic reasoning, might provide indirect tests. Inflation fundamentally changes our conception of the universe's edge. The edge we observe is not the edge of the universe. It's merely the edge of the region that has had time to come into causal contact with us since inflation ended. Beyond this edge lies more universe, potentially infinitely more, governed by the same physics and containing galaxies, stars, and planets we can never observe. The shape of space, geometry, and topology. When we ask about the edge of the universe, we're implicitly assuming the universe has a simple, flat geometry extending in all directions. But general relativity allows for far more exotic possibilities. The universe could be curved, and it could have a complex topology that connects distant regions in unexpected ways. Geometry refers to the curvature of space. There are three basic possibilities: flat, Euclidean, positively curved, like the surface of a sphere, and negatively curved, like a saddle. The curvature is determined by the universe's energy density. If the density equals the critical density, about 5 atoms per cubic meter, plus dark matter and dark energy, space is flat. If density is higher, space is positively curved. If lower, negatively curved. Measurements from the cosmic microwave background indicate the universe is flat to within about 0.4% uncertainty. If there is curvature, it is too small to detect. A flat universe is infinite in extent, assuming it is simply connected. A positively curved universe is finite, but has no edge. Like a sphere's surface, you could travel in a straight line and eventually return to your starting point. A negatively curved universe can be either infinite or finite, depending on its topology. Topology refers to the global structure of space, how different regions connect. Even if space is locally flat, it could have a non-trivial topology. Imagine a video game where moving off the right edge of the screen brings you back on the left. The screen has the topology of a torus, even though it looks flat locally. The universe could have similar properties. It might be a flat torus, a hypersphere, or something more complex. If the universe has a compact topology, it would be finite in volume, even if it has no edge. You could travel in a straight line and eventually return to your starting point after traversing the entire universe. How would we detect non-trivial topology? If the universe is smaller than the observable universe, we might see multiple images of the same galaxy or CMB features in different directions. Light from a galaxy could travel around the universe multiple times, arriving from different angles. Careful analysis of the CMB has searched for such patterns, but found no evidence. This places lower limits on the size of the universe. If it has compact topology, it must be larger than the observable region, at least 46.5 billion light-years across. Some topologies would create edges in a sense. A universe with the topology of a half-space, like the surface of an infinite ocean extending to a shoreline, would have a boundary. But such topologies are considered physically implausible because they would require special boundary conditions and break the homogeneity observed in the universe. The most likely scenario, given current observations, is that the universe is flat or very close to flat, with either infinite extent or a compact topology much larger than the observable region. In either case, there's no edge in the traditional sense. Space simply extends indefinitely, filled with galaxies and structure beyond what we can observe. String theory and other theories of quantum gravity suggest even more exotic possibilities. Space might have extra dimensions beyond the 3 we perceive. These extra dimensions could be compactified, curled up on tiny scales, or extended but hidden from us due to the way matter and energy are confined to a lower dimensional surface, a brane, within higher dimensional space, the bulk. In brane-world scenarios, our universe would be a 3-dimensional surface embedded in a higher dimensional space, and the edge of our universe might be simply the boundary of the brane within the bulk. What lies beyond the observable universe? The most intriguing question about the universe's edge is, what lies beyond? If the observable universe is finite in extent, what exists outside our cosmic horizon? The answer depends on which universe we're talking about. If we mean the entire universe, all of space-time, then by definition, there's nothing outside it. The universe is everything that exists. But if we mean the observable universe, then the answer is more universe, just like what we can see. Beyond our cosmic horizon, there are galaxies, stars, planets, and possibly even civilizations, all governed by the same physical laws. The reason we can't see them is not because they're different or special, but simply because light from them hasn't had time to reach us yet, or because the expansion of space has carried them beyond our event horizon. Cosmological models, particularly those based on inflation, suggest the universe is homogeneous and isotropic on large scales. This means that no matter where you are in the universe, it looks roughly the same. Galaxies are distributed in similar patterns. The CMB has the same average temperature, and the laws of physics are identical. This principle, called the cosmological principle, is supported by observations. The universe looks the same in all directions, with no preferred center or edge. If the cosmological principle holds, then beyond our observable universe, the cosmos continues indefinitely with the same types of structures. There would be galaxy clusters, superclusters, vast voids, and all the phenomena we observe in our local region. Some of those galaxies might host planets with life, perhaps even intelligent civilizations. But we can never observe them, communicate with them, or visit them. They're forever beyond our horizon. There's a subtlety here regarding the distant future. As dark energy drives accelerating expansion, galaxies currently within our observable universe will eventually cross our event horizon and disappear from view. From our perspective, the universe will appear to be shrinking, with fewer and fewer galaxies visible. But from the perspective of those distant galaxies, nothing unusual is happening. They continue existing, evolving, forming stars. The edge is an observational boundary, not a physical one. Some speculative scenarios propose more exotic possibilities. If eternal inflation is correct, our observable universe is one bubble in an infinite multiverse. Other bubbles would have different properties, different values for fundamental constants, different particles, different numbers of dimensions. These other universes would be causally disconnected from ours, separated by regions of eternally inflating spacetime. We could never observe or interact with them, even in principle. Another speculative idea comes from quantum mechanics. Some interpretations of quantum mechanics, particularly the many worlds interpretation, suggest that every quantum event causes the universe to split into multiple branches, each representing a different outcome. In this view, there would be uncountably many parallel universes, all real, all existing simultaneously in a vast quantum multiverse. These parallel universes wouldn't be located beyond our cosmic horizon in space. They'd be orthogonal to our reality in an abstract configuration space called Hilbert space. String theory and M-theory suggest our universe might be one of many branes floating in a higher dimensional bulk. Other branes could exist nearby in the extra dimensions, hosting their own universes with their own physical laws. These parallel universes might interact gravitationally or through other forces that can propagate through the bulk. Some cosmological models propose that the Big Bang was triggered by a collision between branes. While these ideas are fascinating, they're highly speculative and currently untestable. The observable edge of the universe remains a boundary defined by light travel time and cosmic expansion, and what lies beyond is likely just more of the same universe we observe locally. The particle horizon versus the event horizon. Understanding the difference between the particle horizon and the event horizon is crucial for grasping the nature of the universe's edge. Both are cosmological horizons, but they mark different boundaries with different implications. The particle horizon defines the current observable universe. It's the maximum distance from which particles, including photons, could have traveled to reach us since the Big Bang. This horizon grows with time as the universe ages and particles from more distant regions arrive. The particle horizon's radius is currently about 46.5 billion light-years. Mathematically, the particle horizon is calculated by integrating the speed of light over cosmic time, accounting for the expansion of space. In a flat, matter-dominated universe without dark energy, the particle horizon would grow without bound, eventually encompassing arbitrarily large regions. every part of the universe would eventually come into view. But our universe is not matter-dominated. It's dark, energy-dominated, and accelerating. This changes everything. The event horizon marks the boundary beyond which events occurring now will never be observable to us, even if we wait an infinite amount of time. This horizon exists because the accelerating expansion carries distant regions away from us faster than light can travel toward us. The current event horizon is at a co-moving distance of about 16 billion light-years. Galaxies beyond this distance are receding so fast that light emitted by them today cannot reach us. As time passes, the event horizon remains at roughly the same co-moving distance. It shrinks slightly in some coordinate systems, while the particle horizon continues to grow but approaches the event horizon asymptotically. The two horizons will never meet. This has a disturbing implication. There are events happening right now in our universe that we will never be able to observe. A supernova exploding in a galaxy 20 billion light-years away, an alien civilization broadcasting radio signals, a massive black hole merger. None of these events will ever be detectable from Earth, no matter how long we wait or how advanced our technology becomes. The existence of an event horizon fundamentally limits what we can know about the universe. There's a portion of the universe with which we can never interact, never observe, never receive information from. This portion is forever beyond our reach. Interestingly, the event horizon is not symmetric with the past. While there's a future event horizon beyond which we cannot see future events, there's no equivalent past horizon. We can, in principle, observe events from arbitrarily early times, limited only by the opacity of the early universe, not by horizons. This asymmetry arises from the different expansion histories. The universe was decelerating in the past, dominated by matter and radiation, but is accelerating now, dominated by dark energy. The distinction between these horizons matters for different types of observations. Surveys of galaxy distributions probe the particle horizon. We map galaxies out to the edge of what's currently observable. But predictions about the long-term fate of structures in the universe depend on the event horizon. Galaxies beyond the event horizon will eventually fade from view and become unobservable. For gravitational wave astronomy, these horizons have practical implications. LIGO and Virgo detect mergers of stellar mass black holes and neutron stars out to distances of billions of light-years. Future detectors like the Einstein telescope and Cosmic Explorer will reach farther. But there's an ultimate limit. Mergers beyond the event horizon cannot be detected, no matter how sensitive our instruments become. The same applies to electromagnetic astronomy. The James Webb Space Telescope observes galaxies at redshifts approaching 20, corresponding to when the universe was just 200 million years old. Future telescopes might push to 30 or 40, observing the very first stars and galaxies. But there is a limit. We cannot see beyond the cosmic microwave background, 1100, and we cannot see events beyond the event horizon. These horizons also have thermodynamic interpretations. Just as black hole event horizons have temperature and entropy, cosmological horizons in de Sitter space, the type of spacetime dominated by a cosmological constant, have associated temperature and entropy. The entropy of the cosmological horizon is proportional to its area, similar to black hole entropy. This suggests deep connections between gravity, thermodynamics, and quantum mechanics, connections explored in theories like holography and the ADS-CFT correspondence. Redshift, the universe's speedometer. Redshift is one of the most powerful tools in cosmology, allowing us to measure distances to galaxies, determine the expansion rate of the universe, and peer back in time toward the Big Bang. Understanding redshift is essential for understanding the universe's edge. Because redshift tells us how far away objects are and how fast the universe was expanding when their light was emitted. When a light source moves away from an observer, the light's wavelength stretches. It shifts toward the red end of the spectrum. This is the Doppler effect, familiar from the change in pitch of a siren as an ambulance drives past. For galaxies, redshift has two components: the Doppler shift due to the galaxy's motion through space, and the cosmological redshift due to the expansion of space itself. For nearby galaxies, Doppler shift dominates. The Andromeda galaxy, for example, shows a blue shift because it's moving toward us at about 110 kilometers per second, pulled by mutual gravitational attraction. But for distant galaxies, cosmological redshift dominates. The expansion of space stretches the wavelength of light as it travels, independent of the galaxy's motion through space. Cosmological redshift is quantified by the parameter redshift, defined as redshift equals the observed wavelength minus the emitted wavelength divided by the emitted wavelength. A galaxy with redshift equal to 1 has had its light wavelengths doubled by expansion. The universe has expanded by a factor of 1 plus redshift equals 2 since the light was emitted. A galaxy with redshift equal to 2 has had wavelengths tripled. The universe expanded threefold. The highest redshift galaxies observed have redshift greater than 13, meaning the universe has expanded more than 14-fold since their light was emitted. Measuring redshift requires spectroscopy, spreading light into its component wavelengths and identifying specific spectral lines from elements like hydrogen, oxygen, or calcium. Each element absorbs or emits light at characteristic wavelengths. By measuring how much those wavelengths have shifted, we determine the redshift. For very distant galaxies, spectroscopy is challenging because the light is faint and the spectral lines have shifted into infrared wavelengths, requiring specialized instruments. The James Webb Space Telescope, with its powerful infrared capabilities, is revolutionizing high redshift astronomy, detecting galaxies at redshift greater than 10 and enabling detailed spectroscopic studies. Redshift translates to distance through the Hubble relation, but the conversion depends on the universe's expansion history. For nearby galaxies, redshift less than 0.1, Hubble's law applies approximately. Velocity equals the Hubble constant multiplied by distance, and redshift is proportional to velocity. But for distant galaxies, the relationship becomes more complex, depending on the amounts of matter, dark matter, radiation, and dark energy at different cosmic epochs. Cosmologists use the Friedmann equations to calculate the exact relationship between redshift and distance. This requires knowing the cosmological parameters, H0, the matter density, the dark energy density, and the curvature. Measuring the universe. Why the Hubble constant won't sit still. One of the most significant challenges in modern cosmology is the Hubble tension, the discrepancy between different measurements of the Hubble constant. This isn't just a technical problem. It potentially indicates new physics or unknown systematics in our observations. Understanding the Hubble constant is crucial for determining the size of the observable universe and the expansion rate that defines our cosmic horizon. The Hubble constant describes how fast the universe is expanding. Specifically, it gives the recession velocity per unit distance. The Hubble constant, equal to 70 kilometers per second per megaparsec, means that for every megaparsec, 3.26 million light-years of distance, a galaxy recedes 70 kilometers per second faster. The inverse of the Hubble constant gives a rough estimate of the universe's age, the Hubble time, though the actual age differs due to the changing expansion rate over cosmic history. There are two primary methods for measuring the Hubble constant, and they give different answers. The distance ladder method builds up distance measurements from nearby to far. It starts with parallax measurements to nearby stars, uses those to calibrate Cepheid variables, uses Cepheids to calibrate type Ia supernovae, and uses supernovae to measure the expansion rate at large distances. The SH0ES, supernovae Hubble constant for the equation of state collaboration, led by Adam Rees, has refined this method using Hubble Space Telescope observations. Their latest result, the Hubble constant equals 73.04, plus or minus 1.04, kilometers per second per megaparsec. Another method is the early universe method. This method uses observations of the cosmic microwave background. The CMB's temperature fluctuations encode information about the universe's composition and expansion history. By fitting cosmological models to the CMB data, cosmologists can extrapolate forward to calculate the present-day expansion rate. The Planck satellite's measurement gives the Hubble constant equal to 67.4 plus or minus 0.5 kilometers per second per megaparsec. The tension is statistically significant. The two measurements differ by about 9%, and the uncertainties are small enough that this isn't just a statistical fluctuation. Either there are unrecognized systematic errors in one or both methods, or there's new physics that causes the expansion rate to differ between the early universe, CMB, and the present, supernovae. This tension has profound implications for the universe's size and age. If the higher value, 73, is correct, the universe is younger, about 12.6 billion years instead of 13.8 billion years. The observable universe would be slightly smaller. If the lower value, 67, is correct, our current models remain valid. Several proposals attempt to explain the tension. Perhaps there are unrecognized problems with one measurement method. The distance ladder relies on calibrating Cepheids, which could be affected by metallicity or crowding issues. On the other hand, measurements from the cosmic microwave background assume the standard cosmological model, LCDM, which might require modifications. Another possibility is that dark energy existed in the early universe, but was not detectable in the CMB. This early dark energy could influence the expansion history and potentially reconcile the different measurements, though such models are constrained by other observations. It's also possible that general relativity behaves differently on certain scales or at certain epochs, meaning the expansion rate could deviate from current predictions. Some theories of modified gravity are being tested, though most struggle to match all observations. Unknown particles or interactions in the early universe could also play a role. Ideas include sterile neutrinos, modified neutrino properties, or other light particles that could alter the expansion history. Finally, the region of the universe we occupy could be less dense than average, creating a local bias in measurements. However, surveys have not found evidence for such a large void surrounding us. Resolving the Hubble tension is one of cosmology's top priorities. Upcoming missions and surveys will provide independent measurements using different techniques. The Nancy Grace Roman Space Telescope, launching in the late 2020s, will discover thousands of Type Ia supernovae and observe Cepheids in distant galaxies, refining the distance ladder. The Euclid mission will survey billions of galaxies, measuring the expansion history through baryon acoustic oscillations and weak gravitational lensing. The Vera Rubin Observatory will conduct the Legacy Survey of Space and Time, LSST, discovering millions of supernovae and enabling new measurements of cosmic expansion. Gravitational wave standard sirens, mergers of neutron stars detected by LIGO and Virgo, can serve as standard sirens, providing independent distance measurements that don't rely on the distance ladder. The Hubble tension reminds us that cosmology is still an evolving science. Despite extraordinary progress, fundamental questions about the universe's expansion remain unresolved. The edge of the observable universe, its size and rate of growth, depends critically on resolving this tension. The first stars and galaxies, the edge of time. Observing the universe's edge in space is also observing its edge in time. The most distant objects we can see are the earliest structures that formed after the Big Bang. Understanding when and how the first stars and galaxies emerged tells us about the observable universe's ultimate boundary. After recombination at 380,000 years, the universe entered the cosmic dark ages. No stars existed yet, only diffuse neutral hydrogen and helium gas, slowly collapsing under gravity into denser clumps. The universe was dark, except for the fading glow of the CMB, which redshifted from visible light into infrared and eventually microwave wavelengths. The Dark Ages lasted several 100 million years. During this time, gravity pulled gas into the first dark matter halos, concentrations of dark matter that had formed from tiny density fluctuations in the early universe. Gas fell into these halos, heated by compression, and eventually reached densities and temperatures high enough to ignite nuclear fusion. The first stars, called Population 3 stars, were fundamentally different from stars today. They formed from primordial gas containing only hydrogen, helium, and traces of lithium, no heavier elements. Without heavy elements, which astronomers call metals, the gas couldn't cool efficiently. This meant the first stars were much more massive than typical stars today, possibly 100, 300 solar masses, or even larger. These massive stars lived fast and died young, burning through their fuel in just a few million years. They ended their lives in supernova explosions, enriching the surrounding gas with the first heavy elements, carbon, oxygen, iron, and others, synthesized in their cores and during the explosions. These elements would be incorporated into the next generation of stars, beginning the chemical enrichment that would eventually allow planets and life to form. The era of the first stars is called cosmic dawn, or the epoch of reionization. When the first stars ignited, their intense ultraviolet radiation began ionizing the neutral hydrogen around them, creating bubbles of ionized gas. As more stars formed, these bubbles grew and merged, eventually reionizing the entire universe. This process took several 100 million years, ending around redshift equal to 6, about 900 million years after the Big Bang. Evidence for reionization comes from several sources. Spectra of distant quasars show absorption features indicating neutral hydrogen along the line of sight. The pattern of absorption changes with redshift, showing that reionization was largely complete by Z6. The CMB also shows evidence. Reionization scattered some CMB photons, leaving subtle imprints in the CMB polarization. The first galaxies formed shortly after the first stars, as multiple star-forming regions merged into larger structures. These early galaxies were small, chaotic, and rapidly forming stars, nothing like the grand spiral and elliptical galaxies we see today. They were irregular, clumpy, and rich in gas. Observing these first galaxies requires infrared telescopes because their light has been redshifted from ultraviolet and visible wavelengths into infrared. The Hubble Space Telescope pioneered this frontier with the Hubble Ultra Deep Field and subsequent campaigns, discovering galaxies at redshift greater than 10. The James Webb Space Telescope has revolutionized the field, with its large mirror and infrared instruments detecting galaxies at redshift greater than 13 and enabling spectroscopic studies of their properties. JWST observations have revealed surprising results. Galaxies at redshift 10 to 13 are more massive and more mature than expected. Some appear to contain billions of solar masses in stars, with evidence for chemical enrichment, and even supermassive black holes. This challenges models of galaxy formation, which predicted smaller, more primitive galaxies at such early times. These discoveries push the observable universe's temporal edge closer to the Big Bang. Currently, the most distant confirmed galaxies existed when the universe was about 300 million years old, just 2% of its current age. Candidate galaxies at even higher redshifts have been reported, potentially reaching redshift approximately 200 million years after the Big Bang, though these await spectroscopic confirmation. There's a fundamental limit to how early we can observe galaxies: the epoch of the first stars, around redshift approximately 20 to 30. Before this, no stars had formed, and there were no light sources to observe, except the cosmic microwave background. This marks the temporal edge of the luminous universe. Earlier than this, we can only observe through neutrinos, gravitational waves, or the CMB itself. Future missions will continue probing cosmic dawn. The Square Kilometre Array, a massive radio telescope under construction, will map 21-centimeter emission from neutral hydrogen during the Dark Ages and reionization, providing a direct view of the universe before the first stars. Space-based concepts like the Origin Space Telescope or the Habitable Exoplanet Observatory would push infrared observations to even higher redshifts, potentially detecting the very first population 3 stars. The first stars and galaxies represent the beginning of the observable universe as we recognize it, the transition from a dark, uniform cosmos to the rich, complex, structure-filled universe we inhabit. This epoch defines one edge of what we can observe, the transition from the cosmic dark ages to cosmic dawn, from primordial simplicity to emergent complexity. Dark matter, the invisible scaffolding. To understand the universe's structure and its edge, we must confront dark matter, the invisible substance that outweighs ordinary matter by a factor of 5 and provides the gravitational scaffolding upon which galaxies and cosmic structure form. Dark matter was first proposed in the 1930s by astronomer Fritz Zwicky, who studied the motions of galaxies in the Coma cluster. He found that galaxies were moving far too fast to be held together by the gravity of visible matter alone. He calculated that there must be a large amount of unseen dark matter providing additional gravity. The evidence strengthened in the 1970s when Vera Rubin and others measured rotation curves of spiral galaxies. Stars in the outer regions of galaxies were orbiting just as fast as stars near the center, contrary to expectations. If only visible matter were present, orbital velocities should decrease with distance, just as outer planets in our solar system orbit more slowly than inner planets. The flat rotation curves implied that galaxies are embedded in large halos of dark matter, extending far beyond the visible disk. Gravitational lensing provides additional evidence. Massive objects bend space-time, deflecting light from background sources. By mapping how light is distorted around galaxy clusters, astronomers can measure the total mass, both visible and dark. Consistently, the total mass is about 6 times the visible mass, with the excess being dark matter. The cosmic microwave background also reveals dark matter's presence. The pattern of temperature fluctuations in the CMB depends on the balance between ordinary matter, which interacts with radiation, and dark matter, which does not. By fitting models to the CMB data, cosmologists determined that dark matter makes up about 27% of the universe's energy density, compared to just 5% for ordinary matter. Despite overwhelming evidence for dark matter, its true nature remains a mystery. It doesn't emit, absorb, or reflect light, and it doesn't interact through the electromagnetic or strong nuclear forces. Its influence is primarily gravitational, and it might also interact via the weak nuclear force. Among the leading candidates are hypothetical particles known as weakly interacting massive particles, or WIMPs. These would have masses between 10 and 1,000 times that of a proton and interact through gravity and the weak force. Yet decades of searches with underground detectors have found no confirmed signals. Another possibility is axions, extremely light particles first proposed to address a problem in quantum chromodynamics. Produced abundantly in the early universe, they could make up dark matter, and experiments such as AIDMEX are actively searching for them. Some researchers have suggested that primordial black holes, formed within the first fraction of a second after the Big Bang, could account for at least part of dark matter. However, constraints from gravitational lensing, the cosmic microwave background, and other observations rule out most mass ranges for this scenario. Sterile neutrinos offer yet another possibility. These hypothetical particles would interact only through gravity, not the weak force, and would have different effects on cosmology compared to WIMPs. Dark matter plays a crucial role in structure formation. In the early universe, dark matter began clumping under gravity before ordinary matter could. Ordinary matter, interacting with radiation, was prevented from collapsing into dense clumps until after recombination. But dark matter, unaffected by radiation, began forming halos earlier. These halos provided gravitational wells into which ordinary matter later fell, forming stars and galaxies. Computer simulations of cosmic structure formation start with the distribution of dark matter in the early universe and evolve it forward using gravity. These simulations reproduce the large-scale structure of the universe, the distribution of galaxies, galaxy clusters, filaments, and voids, remarkably well. This agreement supports the dark matter paradigm and provides a framework for understanding how the universe evolved from the nearly uniform state observed in the CMB to the complex structure we see today. Dark matter halos extend far beyond the visible parts of galaxies, out to several 100,000 light-years or more. The Milky Way's dark matter halo probably extends to about 600,000 light-years, containing the satellite galaxies and globular clusters that orbit our galaxy. This halo is part of the larger dark matter structure of the local group. On the largest scales, dark matter forms a cosmic web, a network of filaments connecting galaxy clusters with vast voids in between. This web structure is visible in galaxy surveys and is predicted by simulations. The filaments are highways of dark matter along which galaxies form, while voids are underdense regions with few galaxies. Dark matter also affects the universe's edge. The total density of matter, dark plus ordinary, determines whether the universe is open, closed, or flat, with dark matter contributing 27% and ordinary matter 5%. The total is still below the critical density. Dark energy makes up the difference, giving a flat universe. Without dark matter, the universe would be more open, negatively curved, and would expand faster, changing the size of the observable universe. The distribution of dark matter also affects how structure grows over time. Regions with more dark matter grow faster, pulling in more matter and forming larger structures. The rate of structure growth depends on dark matter's properties, specifically whether it's cold, moving slowly, allowing small-scale structure to form, or warm, moving faster, smoothing out small-scale structure. Observations strongly favor cold dark matter, CDM, which allows structures to form hierarchically. Small halos merge to form larger ones, building up galaxies and galaxy clusters over time. This hierarchical model explains the observed distribution of galaxies and the properties of galaxy clusters. Understanding dark matter is essential for understanding the universe's evolution from the uniform early state to the structured cosmos we observe. Dark matter provides the gravitational framework that shapes cosmic structure, from the smallest dwarf galaxies to the largest superclusters. It's the invisible scaffolding that defines the large-scale structure of the universe, extending to the very edge of what we can observe. The multiverse, edges beyond edges. The concept of the multiverse suggests that our universe might be just one among many, perhaps infinitely many. If true, the question of the universe's edge becomes vastly more complex. Instead of one universe with one edge, there could be countless universes, each with its own properties, perhaps even its own physical laws. Several independent lines of theoretical reasoning suggest the possibility of a multiverse. Some models of inflation indicate that inflation never fully ends everywhere. While it stops in regions like ours, producing the hot Big Bang and the universe we observe, other regions continue inflating, creating countless pocket universes scattered through eternally expanding space. Each pocket universe could have different physical properties depending on how the inflaton field decays and what vacuum state the physics settles into. String theory adds another layer to this picture. It allows for an enormous number of possible vacuum states, perhaps 10 to the power of 500 or more, each corresponding to a different set of physical laws, particle masses, and force strengths. If eternal inflation is correct, different pocket universes could settle into different vacua, producing a vast landscape of universes with varied physics. The many worlds interpretation of quantum mechanics offers yet another perspective. According to this view, every quantum measurement causes the universe to branch into multiple versions, one for each possible outcome, meaning countless parallel universes exist simultaneously. Max Tegmark takes the idea even further with the concept of a mathematical universe, proposing that all mathematically consistent structures exist as physical realities, with our universe representing just one structure among infinitely many. Finally, some theorists have considered that if we live in one bubble universe among many, collisions between expanding bubbles could leave observable effects. Such a collision might produce a shockwave and leave a circular pattern in the cosmic microwave background. While searches for these patterns have found no conclusive evidence, they help place limits on how close other bubble universes might be. The multiverse concept is controversial. Critics argue that if other universes are forever beyond our observational horizon, they're not testable and therefore not scientific. If we can never observe or interact with other universes, does it matter whether they exist? Proponents counter that the multiverse is a prediction of theories developed to explain phenomena we do observe. Inflation and string theory were not invented to explain the multiverse. The multiverse fell out of them as a consequence. The multiverse also provides a potential explanation for the fine-tuning problem. Many physical constants and parameters appear finely tuned for life. The strength of gravity, the mass of the electron, the cosmological constant. If any of these were significantly different, stars wouldn't form, atoms wouldn't be stable, or the universe would have collapsed or dispersed before life could arise. In a multiverse, there's no fine-tuning problem. All possible values exist in different universes, and we naturally find ourselves in one where the constants allow life to exist. This is called the Anthropic principle. The Anthropic principle has weak and strong versions. The weak version simply states that we observe what we observe because we exist. We must find ourselves in a universe compatible with our existence. The strong version suggests that the universe must have properties that allow observers to exist at some point. The strong version is more controversial and wades into philosophical territory. If the multiverse exists, what does it mean for the edge of the universe? In the eternal inflation scenario, our observable universe is one bubble in an infinite sea of bubbles, separated by regions of inflating space. The edge of our universe, our cosmic horizon, is the edge of the bubble, or more precisely, the limit of what we can observe within the bubble. Beyond this lie other bubbles, each potentially infinite in extent, each with its own physics. The distance between bubbles is not meaningful in the usual sense, because the intervening space is inflating faster than light. You could never travel from one bubble to another. They're causally disconnected. Events in one cannot influence the other. In this sense, each bubble universe is its own complete cosmos, and the question, what lies beyond our universe, has the answer, other universes, but you can never reach them or observe them. In the quantum many-world scenario, the edge concept is different. Parallel universes exist not in space, but in an abstract configuration space. Every quantum event causes the universe to branch, creating parallel timelines. These parallel universes are not somewhere else in three-dimensional space. They're orthogonal to our reality in Hilbert space. There's no spatial edge separating them. They're separated by quantum decoherence. Multiverse theories challenge our understanding of what universe means. Traditionally, the universe is everything that exists, but in multiverse scenarios, universe refers to our observable region or our causal patch, while multiverse denotes the totality of everything. The edge of our universe is then just the edge of what we can observe, with infinitely more cosmos beyond. The fate of the universe, the ultimate edge in time. Just as we can ask what lies at the edge of the universe in space, we can ask what lies at the edge in time. What is the ultimate fate of the cosmos? Will it expand forever, collapse, or end in some other way? The answer depends on the nature of dark energy and the universe's total content. Current observations indicate that dark energy dominates the universe and is driving accelerating expansion. If dark energy is truly a cosmological constant, energy inherent to space itself with constant density, then the universe will expand forever, accelerating indefinitely. This scenario is called the Big Freeze, or heat death. In the Big Freeze scenario, the universe's future unfolds over timescales almost incomprehensibly long. In the Big Freeze scenario, the universe's future stretches across timescales almost beyond comprehension. Over the next 1 to 100 trillion years, star formation gradually ceases as galaxies exhaust their gas supplies. The universe grows darker as stars burn out, leaving only the longest-lived red dwarfs to shine. Galaxies beyond our local group fade from view, carried beyond our event horizon by accelerating cosmic expansion, leaving the observable universe reduced to just our local gravitationally bound structure. Between 100 trillion and 1 quadrillion years, the last stars finally burn out, and the universe enters the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. Galaxies consist of dead stars orbiting in darkness, with occasional flares from collisions between brown dwarfs or planets becoming increasingly rare. From 1 quadrillion to 1 quintillion years, stellar remnants slowly drift away from galaxies through gravitational interactions. Some stars are ejected into intergalactic space, while others fall towards central supermassive black holes, and over time galaxies dissolve entirely, leaving isolated remnants adrift in an ever-expanding void. Far in the future, around 10 to the power of 40 years and beyond, protons themselves may decay. While the Standard Model treats protons as stable, some extensions of particle physics, particularly grand unified theories, predict proton decay with a half-life between 10 to the power of 34 and 10 to the power of 40 years. Should this occur, all ordinary matter, planets, dead stars, and white dwarfs, would disintegrate into lighter particles and radiation, leaving only black holes, electrons, positrons, neutrinos, and photons. Between 10 to the power of 65 and 10 to the power of 100 years, black holes slowly evaporate through Hawking radiation. This radiation is extremely weak. A solar mass black hole emits at a temperature of just 10 to the power of -7 Kelvin, taking roughly 10 to the power of 67 years to vanish, while supermassive black holes endure far longer. Eventually, all black holes evaporate in a final burst of radiation. Beyond 10 to the power of 100 years, the universe enters the dark era. No stars, planets, or black holes remain. The cosmos becomes a thin, cold soup of photons, electrons, positrons, neutrinos, and perhaps exotic particles spread across ever-expanding space. Temperatures approach absolute zero, and the universe becomes cold, dark, and nearly empty. This is heat death, a state of maximum entropy where no useful energy remains and no complex structures can persist. It is not an end in the sense of time stopping, but a gradual asymptotic approach to a final, unchanging state. However, if dark energy is not constant, other fates are possible. In one scenario, known as the Big Rip, the density of dark energy could increase over time. If its equation of state parameter is less than -1, the accelerating expansion becomes catastrophic. The expansion would grow so fast that it overcomes gravity on all scales, first tearing apart galaxy clusters, then individual galaxies, then solar systems, planets, and eventually even atoms. Ultimately, atomic nuclei could be ripped apart, and space-time itself might be shredded. Depending on how quickly dark energy strengthens, this dramatic end could occur in roughly 100 to 200 billion years. In another possibility, the universe could experience a big crunch. If dark energy weakens, reverses, or if there is more matter than currently estimated, the expansion might slow, stop, and reverse. The universe would begin contracting, with galaxies moving toward one another instead of apart. As contraction continues, galaxies merge, space becomes hotter and denser, and the universe collapses back into a hot, dense state, a reverse of the Big Bang. This could happen tens of billions of years from now. What follows is uncertain, but some theories suggest a bounce, where the universe repeatedly expands and contracts in cycles. A more unsettling prospect comes from quantum field theory, which indicates that what we perceive as empty space might not be in its true lowest energy state. If we live in a false vacuum, it is metastable, but not entirely stable. A quantum fluctuation could trigger a transition to the true vacuum, creating a bubble that expands at the speed of light and destroys everything in its path. Inside the bubble, physical laws would be radically different, with altered particle masses, force strengths, or even numbers of dimensions, making existing matter incompatible with the new vacuum. Vacuum decay could occur at any time, without warning, and there is no way to predict when or if it will happen. Recent calculations suggest the Higgs field, which gives particles mass, might indeed be in such a metastable state. If so, the universe could persist far longer than its current age, perhaps 10 to the power of 100 years or more. But the possibility remains that it could end suddenly and catastrophically through vacuum decay. The ultimate fate depends on measurements of dark energy's properties. The key parameter is W, the ratio of pressure to density. If W equals -1 exactly, cosmological constant, the universe expands forever, ending in heat death. If W is less than -1, phantom energy, the universe ends in a big rip. If W is greater than -1 and evolves appropriately, other outcomes become possible. Current observations constrain W to be very close to -1, consistent with a cosmological constant. The Planck satellite measured W equals -1.03 plus or -0.03. Future missions will measure W more precisely, potentially revealing deviations that indicate how dark energy evolves. The universe's fate also depends on the topology and geometry of space. If the universe is closed, positively curved, it could eventually recollapse even with dark energy, though current observations suggest flat geometry. If the universe has exotic topology, other possibilities emerge, though none change the fundamental outcomes of expansion or contraction. In any scenario except the Big Crunch, the universe has no end in time. It continues expanding forever. The edge in time is not a boundary, but an asymptotic limit, the approach to heat death, maximum entropy, and cold emptiness. This is perhaps more unsettling than a definite ending. The universe doesn't end, it just becomes progressively more dilute, cold, and empty, continuing in that state eternally. Observational limits, what we cannot see. Even with perfect instruments and infinite time, there are fundamental limits to what we can observe about the universe. These limits define absolute edges, boundaries beyond which information cannot reach us, not due to technological constraints, but due to the nature of space-time itself. The most obvious limit in cosmology is the speed of light. Information cannot travel faster than light, so we cannot receive signals from objects whose light has not had time to reach us, defining the particle horizon. Beyond this, accelerating expansion introduces the cosmic event horizon. Objects currently beyond roughly 16 billion light-years are receding so fast that light emitted now will never reach us. And as time passes, more galaxies cross this horizon and fade from view, disappearing forever from our observable universe. At the smallest scales, quantum mechanics and general relativity clash. Distances below the Planck length, around 10 to the -35 meters, and times shorter than the Planck time, about 10 to the -43 seconds, are beyond our theoretical understanding, representing a fundamental edge of knowledge. Observing phenomena at these scales would require a theory uniting quantum mechanics and gravity, something physicists have sought for decades. Black holes present another limit. When matter falls into one, the information about its quantum state appears lost as the black hole evaporates via Hawking radiation, challenging the principle that information is never destroyed. Concepts like holography and the firewall hypothesis aim to resolve this paradox, but no consensus exists. Even at more familiar scales, quantum mechanics imposes intrinsic limits through Heisenberg uncertainty. We cannot simultaneously know a particle's position and momentum with perfect accuracy. This is not a flaw of our instruments, but a fundamental feature of reality. Observationally, we face cosmic variance because we have access to only one universe. Some properties of the cosmos were set by random quantum fluctuations in the early universe, and without the ability to sample multiple universes, some uncertainty is unavoidable. Opaque epochs further restrict what we can see. Before recombination, the universe was opaque to light, meaning electromagnetic astronomy cannot probe earlier times. Observing earlier epochs requires alternative messengers like neutrinos, gravitational waves, or exotic particles, but each comes with its own limits. Gravitational waves, for instance, can travel through the early opaque universe and might reveal information from the first fraction of a second, but detectors are sensitive only to certain frequency ranges, and primordial waves from inflation are extremely weak. Similarly, the cosmic neutrino background could extend our observational reach beyond the cosmic microwave background. Yet detecting these elusive neutrinos requires massive instruments and long observation times. Dark matter illustrates another practical limit. Despite overwhelming indirect evidence, it has never been directly detected in laboratories. If dark matter interacts only gravitationally, or if its interaction cross-section is below current detection capabilities, it may remain forever beyond direct observation, known only through its gravitational influence. On a more conceptual level, quantum decoherence sets an edge between the microscopic and macroscopic worlds. Quantum superposition exists until measured, but for large systems, decoherence occurs almost instantly due to environmental interactions, making it impossible to observe quantum phenomena in everyday objects. Across scales, from the fastest to the slowest, the largest to the smallest, the observable to the theoretical, the universe sets boundaries on what can be known, leaving fundamental edges that may never be crossed. These limits collectively define the edges of the knowable universe. Some are technological and might be overcome with better instruments. Others are fundamental, imposed by the laws of physics themselves. Understanding these limits is as important as understanding what we can observe. They tell us what questions are answerable and what must remain mysteries. The Anthropic principle, why this universe? The Anthropic principle arises from a striking observation. The universe appears finely tuned for life. Many physical constants and parameters must fall within extremely narrow ranges for stars, planets, and life to exist. Even small deviations in these values would render the universe uninhabitable, raising the profound question of why the cosmos is set up the way it is. Take the cosmological constant, for example. Dark energy's density is roughly 10 to the negative 120 in Planck units, while quantum field theory predicts it should be 10 to 120 times larger. If it were slightly larger than observed, the universe would have expanded so rapidly that galaxies could never form. If negative and comparably large, the universe would have collapsed before stars could ignite. Its observed value falls in an extraordinarily narrow window that permits the formation of structure. The strong nuclear force shows similar precision. This force binds quarks into protons and neutrons and binds these into atomic nuclei. A mere 2% weaker, and deuterium would be unstable, halting the nuclear reactions in stars that produce heavier elements. 2% stronger, and protons would bind into pairs during the Big Bang, leaving no free hydrogen to form stars. Other constants demonstrate comparable sensitivity. The fine structure constant, approximately 1/137, governs the strength of electromagnetic interactions. Even slight changes would shift atomic energy levels, disrupting stable atoms and chemical bonding. The electron-to-proton mass ratio, currently about 1,836, also matters profoundly. A significantly different ratio could make atoms too large or prevent stable molecules, fundamentally altering chemistry. Carbon production in stars depends on the carbon-12 nuclear resonance at 7.654 megaelectronvolts. This precise energy level enables the triple alpha process, fusing helium into carbon. Without it, carbon-based life might never arise, a fact Fred Hoyle famously predicted using anthropic reasoning. Gravity too must be finely balanced. Its strength sets stellar lifetimes and the equilibrium between radiation pressure and gravitational collapse. Stronger gravity would burn stars out in millions of years, leaving insufficient time for life, while weaker gravity might prevent stars from igniting altogether. Finally, the universe's initial density fluctuations, about 1 part in 100,000, are critical. Smaller fluctuations would fail to form galaxies or stars, while larger ones could lead to a universe dominated by black holes, leaving no stable structures for life. Taken together, these examples illustrate how the cosmos exists within an extraordinarily narrow set of parameters that allow observers like us to emerge. The anthropic principle attempts to explain this fine-tuning. The weak anthropic principle states that we observe what we observe because we exist. We must find ourselves in a universe compatible with our existence. This is a tautology, but has predictive power. In a multiverse where different regions have different physical constants, intelligent observers will necessarily find themselves in regions where constants allow life. The strong anthropic principle suggests the universe must have properties allowing observers to exist at some point. This version is more controversial, implying purpose or design, and is generally disfavored by physicists. The anthropic principle gains explanatory power when combined with multiverse theories. If eternal inflation or the string landscape produces countless universes with different constants, fine-tuning is explained through selection. We observe a life-permitting universe because we couldn't exist in any other kind. The vast majority of universes might be sterile, but that doesn't matter. Observers only arise in the rare regions where conditions are right. Critics argue that anthropic reasoning is unfalsifiable. If we can't observe other universes, we can't test whether they have different physical constants. The multiverse becomes an untestable hypothesis used to explain fine-tuning. Proponents counter that the multiverse is predicted by theories developed for other reasons, inflation, string theory, not invented solely to solve fine-tuning. Some physicists seek alternatives to anthropic explanations. Perhaps there's a deeper theory that explains why constants have their observed values, making them not arbitrary but determined by fundamental principles we don't yet understand. String theory might eventually provide such a theory, deriving all constants from a unique mathematical structure. If so, fine-tuning would be an illusion. The constants couldn't be any other way. Another approach is the principle of mediocrity. We should not assume we're special or privileged. If observers exist throughout the universe or multiverse, we should expect to find ourselves in a typical location. This principle can make predictions. For example, if the cosmological constant varies across a multiverse, typical observers should find themselves in regions where the constant is not too far from the minimum value, allowing structure formation. The observed value is indeed close to this minimum, consistent with the prediction. The anthropic principle also connects to the question of the universe's edge. If we live in a multiverse, the observable universe's edge is just the boundary of one region among many. Beyond our horizon lie other regions, potentially with different physics. The constants that make our region habitable might be different elsewhere, making those regions unable to support life or even stable matter. This raises philosophical questions. Is the multiverse real if it's forever unobservable? Does it matter whether other universes exist if we can never interact with them? These questions blur the line between physics and philosophy, touching on the nature of reality, existence, and the limits of science. Quantum fluctuations and the Big Bang. The universe's beginning, the Big Bang, represents the ultimate edge in time. But what caused the Big Bang? What happened before it? Modern cosmology, combining quantum mechanics and general relativity, offers tantalizing hints. The classical Big Bang model extrapolates the universe's expansion backward in time to a singularity, a point of infinite density and temperature where space-time curvature becomes infinite. General relativity predicts this singularity, but it also breaks down there. At the singularity, equations produce infinities, signaling that the theory is incomplete. We need quantum gravity to describe what happens at the universe's beginning. several quantum approaches to cosmology have been developed. Quantum cosmology. In the 1980s, James Hartle and Stephen Hawking proposed the no-boundary proposal. They applied quantum mechanics to the entire universe, describing its wave function. In this framework, time emerges from a quantum state that has no boundary in the past, no beginning. Time becomes purely imaginary, in the mathematical sense, near the Big Bang, and the question, what happened before, becomes meaningless, like asking what's north of the North Pole. Loop quantum cosmology. This approach, derived from loop quantum gravity, suggests that quantum effects prevent the singularity. As density and curvature increase toward the Planck scale, quantum repulsion overcomes gravitational attraction, causing a bounce. The universe contracts to a minimum size, then rebounds in an expanding phase, the Big Bang. Before the bounce, there was a previous contracting phase, potentially another universe. This leads to a cyclic model where universes expand, contract, bounce, and expand again indefinitely. Eternal inflation and tunneling from nothing. In this scenario, the universe begins as a quantum fluctuation from nothing, a state with no space, time, matter, or energy. Quantum uncertainty allows such fluctuations. A tiny region of space spontaneously appears, in an inflating state with high vacuum energy. This inflating patch grows exponentially, eventually transitioning to a hot Big Bang phase. The probability of such a fluctuation is extraordinarily small, but in an infinite quantum ensemble, it becomes inevitable. These scenarios share a common theme. Quantum mechanics is essential for understanding the universe's origin. Classical general relativity predicts a singularity, but quantum effects modify the physics at extreme densities and short times, potentially eliminating the singularity or rendering the question of before the Big Bang ill-defined. Quantum fluctuations also play a role in generating the seeds of cosmic structure. During inflation, quantum vacuum fluctuations are stretched to macroscopic scales, creating slight overdensities and underdensities in the inflaton field. When inflation ends and the inflaton decays, these fluctuations become density perturbations in ordinary matter and radiation. Gravity amplifies these perturbations over billions of years, growing them into galaxies, clusters, and the cosmic web. The connection between quantum mechanics and cosmology is profound. The largest structures in the universe, superclusters spanning hundreds of millions of light-years, originated from quantum fluctuations smaller than an atom. This is one of the most remarkable predictions of inflationary cosmology, confirmed by observations of the CMB and large-scale structure. Quantum fluctuations also set limits on observability. Heisenberg's uncertainty principle states that energy and time cannot both be precisely defined. The change in energy multiplied by the change in time is greater than or equal to the reduced Planck constant divided by 2, where the reduced Planck constant is denoted by h bar. This implies that at very short timescales, energy fluctuations are large. At the Planck time, 10 to the negative 43 seconds, energy fluctuations become so large that space-time itself becomes uncertain, a quantum foam of fluctuating geometry. We cannot probe physics before the Planck time because our theories break down. This represents an absolute edge in time, not a moment when the universe began, but a boundary of theoretical knowledge. Understanding what happens at the Planck scale requires a theory of quantum gravity, which physicists have been seeking for decades. String theory and loop quantum gravity are leading candidates, but neither is complete or empirically confirmed. String theory suggests that at the Planck scale, space-time consists of tiny vibrating strings or higher dimensional membranes. Loop quantum gravity proposes that space-time itself is quantized, made of discrete loops at the Planck scale. Both theories predict modifications to general relativity at extreme energies, potentially eliminating singularities. The universe's beginning might not be a beginning at all, but a transition from a previous state. In cyclic models, the Big Bang is a bounce from a contracting phase. In eternal inflation, The Big Bang is one phase transition among many in an eternally inflating multiverse. In quantum cosmology, time itself emerges from a timeless quantum state, making beginning a concept that doesn't apply. This fundamentally changes the question of the universe's edge in time. Rather than asking, when did the universe begin, we might ask, what is the nature of the quantum state from which space-time emerges? Or, what existed before inflation? These are deep questions at the frontier of theoretical physics, where cosmology meets quantum gravity. The search for extra dimensions. String theory and related frameworks suggest that space might have more than 3 dimensions. If extra dimensions exist, they would fundamentally alter our understanding of the universe's structure and its edge. These extra dimensions could be compactified, curled up on microscopic scales, extended but hidden, or part of a higher dimensional space in which our universe is embedded. The idea of extra dimensions has a long history. In 1919, Theodore Kaluza proposed a 5-dimensional theory unifying gravity and electromagnetism. Oscar Klein developed the idea further, suggesting the 5th dimension is compactified, curled up into a tiny circle too small to observe. This Kaluza-Klein theory was elegant, but ultimately unsuccessful at explaining particle physics. Modern string theory requires extra dimensions for mathematical consistency. Superstring theory requires 10 dimensions, 3 spatial, 1 temporal, and 6 extra-spatial dimensions. M-theory, which unifies different versions of string theory, requires 11 dimensions. These extra dimensions must be compactified to scales around the Planck length, 10 to the power of minus 35 meters, to be consistent with observations. The geometry of compactification determines the physics of our 4-dimensional world. Different compactification schemes produce different particle spectra and force strengths. This is the origin of the string landscape. The vast number of possible compactifications, each corresponding to a different vacuum state with different physical laws. But extra dimensions might not be fully compactified. Some models propose large extra dimensions, dimensions with sizes much larger than the Planck scale, potentially even millimeters. In these models, gravity can propagate through all dimensions, but other forces are confined to a lower dimensional surface, a brane. We live on a 3-dimensional brane, embedded in higher dimensional space, the bulk. Large extra dimensions would modify gravity at small scales. Below the size of the extra dimensions, gravity becomes stronger than expected from the inverse square law. Experiments testing gravity at sub-millimeter scales have searched for deviations but found none, placing limits on the size of potential extra dimensions. If extra dimensions exist, they could connect distant regions of our universe in unexpected ways. Wormholes, shortcuts through higher dimensional space, might link regions that are far apart in our 3 dimensions, but close in the bulk. These wormholes could provide routes to otherwise unreachable parts of the universe, effectively bypassing the cosmic horizon. However, wormholes as shortcuts are purely speculative. General relativity allows wormhole solutions, but they require exotic matter with negative energy density to remain open. No such matter has been discovered, and quantum field theory suggests that maintaining a traversable wormhole requires conditions that might be impossible to achieve. Extra dimensions also appear in brane world scenarios. If our universe is a 3-dimensional brane in higher dimensional space, other branes might exist nearby, in the extra dimensions. These parallel branes would be entire universes, separate from ours but potentially interacting gravitationally. Collisions between branes might trigger Big Bang-like events, and gravitational waves could propagate through the bulk, potentially allowing indirect detection of other branes. The Large Hadron Collider has searched for evidence of extra dimensions. If extra dimensions exist with sizes around 10 to the negative 19th meters or larger, the collider might produce microscopic black holes in high-energy collisions. These black holes would evaporate instantly through Hawking radiation, producing distinctive signatures. No such events have been observed, placing limits on the size and number of extra dimensions. Extra dimensions also affect the expansion of the universe. If gravity propagates in extra dimensions, the expansion rate depends on the geometry of those dimensions. Observations of the expansion history constrain models with extra dimensions, requiring that any extra dimensions are either very small or have specific geometries that reproduce observed cosmology. The concept of extra dimensions fundamentally changes the meaning of the edge of the universe. If our three-dimensional space is embedded in a higher dimensional bulk, the edge might not be a boundary in our dimensions, but a location in the bulk. Our universe could be finite in extent within the bulk, like a sheet of paper floating in a three-dimensional room. Moving to the edge wouldn't mean reaching a wall in our three dimensions. It might mean moving in directions we cannot directly perceive. Despite decades of research, extra dimensions remain hypothetical. No direct evidence exists, and string theory makes no testable predictions that uniquely confirm extra dimensions. But mathematics is compelling, and extra dimensions solve certain theoretical problems. The search continues through high-energy experiments, precision gravity measurements, and cosmological observations. Gravitational waves, a new window on the edge. Gravitational waves, ripples in spacetime predicted by Einstein and detected in 2015, provide a new way to observe the universe. Unlike light, gravitational waves pass through matter almost unimpeded, allowing observations of events and epochs that are opaque to electromagnetic radiation. This opens possibilities for probing closer to the edge of the observable universe and earlier in time than ever before. The first gravitational wave detection, announced by LIGO in February 2016, came from the merger of two stellar mass black holes 1.3 billion light-years away. Since then, LIGO and its partner Virgo have detected dozens of mergers involving black holes and neutron stars. These detections inaugurated gravitational wave astronomy as a new field. Gravitational waves carry information unavailable through electromagnetic observations. When two black holes merge, they produce no light, only gravitational waves. Observing these waves tells us about the masses and spins of the black holes, the merger dynamics, and tests of general relativity in the strong field regime. This is information that would be completely inaccessible through optical or radio telescopes. Gravitational waves provide cosmology with a set of unique tools that complement traditional observations. When neutron stars merge, they produce both gravitational waves and electromagnetic radiation, known as a kilonova. By analyzing the gravitational wave signal, we can determine the distance to the merger directly, without relying on the conventional distance ladder. Measuring the redshift from the electromagnetic counterpart then reveals how fast the source is receding, and combining these measurements provides an independent way to determine the Hubble constant, offering potential insight into the Hubble tension. Gravitational waves also offer a window into the very early universe. Quantum fluctuations during inflation are expected to generate primordial gravitational waves, which would leave an imprint on the cosmic microwave background in the form of B-mode polarization. Detecting this signal would confirm the inflationary paradigm, measure the energy scale of inflation, and give access to physics at energies around 10 to the 16th giga-electronvolts, far beyond the reach of any particle accelerator. Beyond individual events, the universe is filled with a stochastic background of gravitational waves from countless unresolved sources, including ancient black hole mergers, phase transitions in the early universe, and hypothetical phenomena like cosmic strings. Observing this background would provide a record of the universe's history that is inaccessible through single sources. Gravitational waves also allow us to study the evolution of black hole populations over cosmic time. By detecting mergers at different redshifts, we can trace how stellar mass black holes formed and evolved, how common mergers are, and how these processes relate to galaxy formation and stellar evolution. In these ways, gravitational waves open an entirely new observational window on the cosmos, revealing both its distant past and its hidden dynamics. future gravitational wave detectors will dramatically expand these capabilities. The Einstein Telescope and Cosmic Explorer next-generation ground-based detectors planned for the 2030s will be 10 times more sensitive than current detectors, and will observe mergers out to redshifts greater than 10, seeing black hole populations from the universe's first billion years. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect low-frequency gravitational waves from supermassive black hole mergers. These events, involving black holes millions to billions of solar masses, are too low in frequency for ground-based detectors, but will be loud and clear for LISA. LISA will detect mergers across cosmic time, mapping how supermassive black holes grew and merged as galaxies evolved. LISA might also detect gravitational waves from the early universe, from phase transitions when forces separated, from cosmic strings, if they exist, or from other exotic sources. These signals would probe the universe at energies and epochs inaccessible to any other observation method. Pulsar timing arrays, which use the galaxy's pulsars as a giant gravitational wave detector, are on the cusp of detecting low-frequency gravitational waves from supermassive black hole binaries. Several groups reported evidence for a gravitational wave background in 2023, consistent with the population of merging supermassive black hole binaries. Confirmation and characterization of this signal will reveal how often supermassive black holes merge and test models of galaxy evolution. Gravitational waves could probe the universe before the CMB. While photons couldn't travel freely before recombination, 380,000 years after the Big Bang, gravitational waves could. In principle, detecting gravitational waves from the first second of the universe would allow direct observation of Big Bang nucleosynthesis, the quark-gluon plasma, or even earlier epochs. This would push the observational edge of the universe much closer to the beginning. There's even speculation about detecting gravitational waves from inflation itself. If inflation ended with violent oscillations of the inflation field, or if it involved phase transitions, it might have produced detectable gravitational waves. These waves would have extraordinarily long wavelengths, potentially light years across, but they might be detectable through their effect on the orbits of pulsars or spacecraft. Gravitational wave astronomy is still in its infancy, but it's already transforming our view of the universe. As detectors improve and new types come online, gravitational waves will become an increasingly powerful tool for exploring the universe's edge in space, in time, and in energy. The Fermi paradox and cosmic horizons. The Fermi paradox asks, if the universe is vast and old, why haven't we detected signs of extraterrestrial civilizations? This question connects to the universe's edge in surprising ways. If intelligent life is common, civilizations might exist beyond our cosmic horizon, forever undetectable, regardless of how advanced they or we become. The Drake equation attempts to estimate the number of communicating civilizations in the galaxy. The Drake equation attempts to estimate the number of communicating civilizations in the galaxy. N equals R star multiplied by F sub P multiplied by N sub E multiplied by F sub L multiplied by F sub I multiplied by F sub C multiplied by L. The equation incorporates several key variables that estimate the potential number of technologically advanced civilizations in our galaxy. Here, R star represents the rate of star formation, indicating how many new stars form per year. F sub P is the fraction of those stars that have planetary systems, while N sub A denotes the average number of planets per system that could potentially support life. F sub L refers to the fraction of those planets where life actually emerges, and F sub I represents the fraction of life-bearing planets where intelligent life evolves. F sub C is the fraction of intelligent civilizations that develop technology capable of interstellar communication. Finally, L stands for the average lifetime of such civilizations, the length of time they are able to send detectable signals into space. Together, these parameters form the basis of the Drake equation, a probabilistic framework for estimating the likelihood of extraterrestrial civilizations. Estimates vary wildly depending on assumptions. Optimistic values suggest thousands of civilizations in the galaxy. Pessimistic values suggest we might be alone. But even if civilizations are common, cosmic expansion limits how many we could ever contact. Light from a civilization 16 billion light-years away, beyond our event horizon, will never reach us. Even if they broadcast powerful radio signals, those signals are being carried away from us by accelerating expansion faster than they can travel toward us. Countless civilizations might exist beyond our horizon, engaged in interstellar commerce, building megastructures, and exploring their regions of the universe. Yet we will never know they exist. This creates what might be called the cosmic loneliness problem. Even if the universe teems with life, the accelerating expansion ensures that most civilizations will never contact each other. Each civilization is confined to its cosmic horizon, which spans billions of Lig cosmologists use the Friedmann equations to calculate the exact relationship between redshift and distance. This requires knowing the cosmological parameters: H arrow, the matter density, the dark energy density, and the curvature. With these parameters constrained by observations from the CMB, supernovae, and galaxy surveys, we can convert any redshift to a distance and a look-back time, how long ago the light was emitted. The cosmic microwave background has a redshift of approximately 1100. This corresponds to a look-back time of 13.8 billion years, minus 380,000 years, essentially the entire age of the universe. The CMB photons have been traveling through space for 13.8 billion years, but due to cosmic expansion, they were emitted from locations now 46.5 billion light-years away. Redshift also allows us to map the universe's expansion history. By measuring redshifts and distances to many galaxies at different epochs, cosmologists can reconstruct how fast the universe was expanding at each point in time. The supernova observations that discovered dark energy used this technique. Distant supernovae had redshifts, indicating they were farther away than expected in a decelerating universe, proving that expansion was accelerating. There is a limit to how much redshift we can observe. At a redshift of approximately 1100, corresponding to the cosmic microwave background, the universe becomes opaque to electromagnetic radiation. But there is another type of horizon encoded in redshift. Objects beyond the event horizon have effectively infinite future redshift. We will never see them, so their redshift is undefined or approaches infinity. Objects just inside the event horizon have very high redshifts and are fading from view as accelerating expansion carries them away. Redshift has another important property. It is directly related to the scale factor of the universe, denoted A of t, which describes how much the universe has expanded at time t. The scale factor is normalized to A equals 1 today. At earlier times, A is less than 1. The universe was smaller. The relationship is simple. 1 plus z equals 1 divided by A. So a redshift of 1 corresponds to A equals 1/2. The universe was half its current size. The cosmic microwave background, at a redshift of approximately 1100, corresponds to approximately 1/1100. The universe was about 1,000 times smaller in linear dimension, or roughly a billion times smaller in volume. Understanding redshift is essential for interpreting observations of distant objects. When we observe a galaxy at a redshift of 6, we are seeing it as it was when the universe was only about 900 million years old, just 6.5% of its current age. The galaxy has evolved significantly since then. The stars we see in that ancient image have long since died. New generations of stars have formed, and the galaxy itself may have merged with others, grown larger and changed its structure. We are seeing a snapshot of a much younger universe. This time travel aspect of astronomy gives us a unique perspective on cosmic evolution. By observing galaxies at different redshifts, we see the universe at different ages, watching how galaxies, stars, and large-scale structures change over billions of years. Nearby galaxies, at a redshift of approximately 0, show us the present-day universe, Galaxies at redshifts of about 1 to 3 show us the universe during its most active phase of star formation. Galaxies at redshifts greater than 6 show us the universe when the first stars and galaxies were forming, still emerging from the cosmic dark ages. Redshift surveys, which measure the positions and redshifts of millions of galaxies, create three-dimensional maps of the universe. These maps reveal the large-scale structure, galaxy clusters, filaments, and voids. By comparing maps at different redshifts, different epochs, cosmologists track how structure grows over time, testing models of gravity and dark matter. The most distant confirmed galaxies and quasars have redshifts around 13 to 14. These objects existed when the universe was just 300 to 400 million years old. Observing them tests our understanding of how quickly galaxies formed after the Big Bang, and how supermassive black holes grew to billions of solar masses so early in cosmic history. The James Webb Space Telescope is discovering candidates with even higher redshifts, potentially 16 to 20, pushing observations to within 200 million years of the Big Bang. There is a theoretical limit to observable redshift. The first stars, sometimes called population 3 stars, formed at redshifts of approximately 20 to 30, perhaps 100 to 200 million years after the Big Bang. Before this epoch, the universe was dark. No stars or galaxies had yet formed. This era, called the Cosmic Dark Ages, lasted from recombination at a redshift of approximately 1100 until the first stars ignited. During the Dark Ages, the universe was filled with neutral hydrogen gas, opaque to visible light but transparent to longer wavelengths. We can potentially observe this epoch through 21 centimeter radio emission from neutral hydrogen, though no detections have been confirmed yet. Redshift thus provides both a distance measure and a time coordinate. It's the primary tool for mapping the universe's edge, allowing us to trace the observable universe from nearby galaxies to the CMB from the present day back to 380,000 years after the Big Bang. Every increase in observable redshift pushes the boundary of the known universe farther back in time and farther out in space. Quantum entanglement and non-locality, connections across the edge. Quantum mechanics introduces phenomena that seem to defy the cosmic speed limit and the boundaries imposed by horizons. Quantum entanglement, in particular, creates correlations between particles that persist instantaneously across arbitrary distances. This raises fascinating questions about the nature of the universe's edge and whether quantum mechanics provides loopholes in the restrictions imposed by relativity and cosmic expansion. Entanglement occurs when two or more particles interact in such a way that the quantum state of each particle cannot be described independently. Instead, they share a joint quantum state. When you measure one particle and find it in a particular state, the other particle instantaneously assumes a correlated state, regardless of the distance between them. This spooky action at a distance, as Einstein called it, troubled him deeply. It seemed to violate the principle that nothing can travel faster than light. How can measuring one particle instantly affect another particle light years away? Einstein proposed that quantum mechanics was incomplete, and that hidden variables must carry information between the particles at sublight speeds. In the 1960s, physicist John Bell developed a theorem showing that any theory with local hidden variables would produce different statistical predictions than quantum mechanics. Experiments testing Bell's inequalities consistently confirm quantum mechanics and rule out local hidden variable theories. Entanglement is real, and the correlations are genuinely instantaneous. However, and this is crucial, entanglement cannot be used to transmit information faster than light. When you measure an entangled particle, you get a random result. The correlation with the distant particle only becomes apparent when you compare measurements, which requires sending classical information at light speed or slower. Entanglement provides correlation without causation. It doesn't violate relativity's prohibition on faster-than-light signaling. This has profound implications for cosmic horizons. Consider two particles that become entangled in the early universe. As the universe expands, the particles are carried to opposite sides of the observable universe, eventually crossing each other's event horizons. They are now in causally disconnected regions. No signal from one can reach the other. Yet the entanglement persists. If someone in one region measures their particle, quantum mechanics predicts that the other particle, beyond the horizon, instantaneously assumes a correlated state. The correlation exists, but it cannot be used to send messages or transfer information between the disconnected regions. Each observer sees random results. Only if they could compare notes, which they can't due to the horizon, would the correlation become apparent. This suggests that quantum mechanics encodes connections that transcend the classical notion of causality and horizons. Entanglement is non-local. It doesn't respect spatial separation. Yet it also doesn't violate causality in the sense of allowing faster-than-light communication. It's a deeply subtle phenomenon that reveals the universe's quantum nature. Some physicists speculate that entanglement might play a fundamental role in the structure of spacetime itself. In recent years, research in quantum gravity has explored the idea that spacetime emerges from quantum entanglement. In this view, the fabric of space is woven from entanglement between quantum degrees of freedom. Regions with high entanglement correspond to smooth connected spacetime. Regions with low entanglement are disconnected or have exotic geometry. This is the principle behind the ER is equal to EPR conjecture, proposed by Juan Maldacena and Leonard Susskind. ER refers to Einstein-Rosen bridges, wormholes, while EPR refers to the Einstein-Podolsky-Rosen paradox, entanglement. The conjecture suggests that entangled particles are connected by tiny, non-traversable wormholes through spacetime. Entanglement and wormhole geometry are two descriptions of the same phenomenon. If ER is equal to EPR is correct, then entangled particles beyond the cosmic horizon are connected by wormholes through higher dimensional space or through the quantum structure of spacetime. These connections exist at a level deeper than classical spacetime, suggesting that cosmic horizons are classical boundaries that don't fully capture the quantum structure of reality. Entanglement also appears in the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. This principle arose from studies of black hole entropy and has been extended to cosmology. In some models, the observable universe is a holographic projection of information encoded on the cosmic horizon. The horizon is not just a boundary, but a fundamental surface where information about the entire observable universe resides. If the holographic principle applies to cosmology, then the cosmic horizon has a finite information content, proportional to its area. This sets a limit on the number of distinguishable quantum states in the observable universe, a limit on how much information can exist or be processed. As the universe expands and the horizon grows, the information capacity increases, but it remains finite at any given time. Entanglement is key to understanding this information structure. The quantum states inside the horizon are entangled with states outside, and the entropy of the horizon reflects the amount of this entanglement. In this picture, the cosmic horizon is not merely an observational boundary, but a deep feature of quantum spacetime, encoding information about both the observable universe and what lies beyond. Quantum field theory in curved spacetime, the framework combining quantum mechanics with general relativity, predicts that observers in accelerating reference frames or near horizons experience thermodynamic effects. Just as Hawking radiation causes black holes to have temperature, the cosmic horizon in an accelerating universe has a temperature called de Sitter temperature. This temperature is extraordinarily small, about 10 circumflex 30 Kelvin, but it's non-zero in principle. This temperature is associated with quantum fluctuations near the horizon. Virtual particle pairs pop into existence from the vacuum. Normally they annihilate almost immediately. But near the horizon, one particle can fall beyond the horizon while the other remains inside. To an observer inside the horizon, this appears as thermal radiation emanating from the horizon, similar to Hawking radiation from black holes. The existence of this radiation suggests that cosmic horizons have thermodynamic properties, temperature and entropy, just like black holes. This is part of a broader pattern in gravitational physics. Horizons of all types, black holes, cosmological, Rindler, have associated thermodynamics. This hints at a deep connection between gravity, quantum mechanics, and information theory, one that physicists are still working to fully understand. Quantum mechanics also affects the initial conditions of the universe. Inflation amplifies quantum fluctuations to cosmic scales, creating the seeds of structure. These fluctuations are quantum mechanical in origin, governed by Heisenberg's uncertainty principle. The distribution of galaxies across the observable universe, and presumably beyond the horizon, reflects quantum randomness from the inflationary epoch. This means the large-scale structure of the universe, including regions beyond our horizon, is fundamentally quantum mechanical. Classical physics would predict a smooth, uniform cosmos. Quantum mechanics introduces the irregularities that make the universe interesting, the density fluctuations that grew into galaxies, stars, planets, and ultimately life. Entanglement might even connect our observable universe to regions beyond the horizon or to other universes in a multiverse. If the multiverse arises from eternal inflation, different bubble universes might be quantum entangled if they originated from correlated quantum fluctuations in the inflating background. These correlations would persist even as the bubbles become causally disconnected. Such entanglement across cosmic horizons or between separate universes would be unobservable in any direct sense. We can't measure particles beyond the horizon or in other universes. But it raises deep questions about the nature of reality. If quantum states extend beyond observational horizons, binding distant regions, or separate universes in a quantum whole, then the universe is more interconnected than classical space-time geometry suggests. The edge of the universe, from a quantum perspective, is not a sharp boundary, but a complex, entangled interface. Classical general relativity describes horizons as limits of causal influence. Quantum mechanics suggests a subtler picture. Horizons as boundaries of classical information flow, but with quantum correlations persisting across them. The full nature of these boundaries awaits a complete theory of quantum gravity, which would unify quantum mechanics and general relativity into a single framework describing the universe at all scales, from the Planck length to the cosmic horizon. The philosophy of the edge. What does it mean to exist beyond observation? Throughout this exploration of the universe's edge, we've encountered a recurring theme. There are regions of reality that we cannot observe, even in principle. Beyond the cosmic horizon lie galaxies we will never see. Before the Planck time lies physics we cannot describe. In the multiverse scenarios, entire universes exist that we can never detect. This raises profound philosophical questions. If something cannot be observed, does it exist? What does it mean for something to be real if it's forever beyond our ability to verify? These questions touch on fundamental issues in philosophy of science. Science is built on empirical observation and testability. Theories make predictions that can be tested through experiment or observation. If a theory predicts unobservable entities, regions beyond horizons, other universes, physics below the Planck scale, is it still scientific? Or has it crossed into metaphysics? Some physicists and philosophers argue that unobservable entities are legitimate if their predictions of theories developed to explain observable phenomena. Inflation, for example, was proposed to solve specific problems in cosmology, the horizon problem, flatness problem, and others. The theory makes testable predictions about the CMB's properties, predictions that have been confirmed. That inflation also predicts a vastly larger universe beyond our horizon, or potentially a multiverse, is a consequence of the same theory. We didn't invent inflation to postulate unobservable regions. Those regions fell out as predictions. Similarly, The cosmic event horizon is a prediction of general relativity combined with observations of accelerating expansion. We don't observe the horizon directly, we can't visit it or see what lies beyond. But we observe the expansion, we measure dark energy's properties, and general relativity predicts that these conditions create an event horizon. Accepting general relativity as our theory of gravity means accepting its predictions, even when they involve unobservable regions. This view holds that reality extends beyond observation. The universe doesn't end at our horizon. It continues, filled with galaxies, stars, and structure, just like what we observe locally. Our inability to see those distant regions is a limitation of our position in space-time, not a statement about whether they exist. An observer in one of those distant galaxies would see their own observable universe, overlapping partially with ours, but extending in different directions. From their perspective, we are beyond their horizon, yet we certainly exist. This leads to a form of scientific realism. The belief that the universe exists independently of our observations, that scientific theories describe objective reality, and that theoretical entities, even unobservable ones, are real if they're part of our best theories. Most working physicists implicitly adopt this view. They believe that galaxies beyond the horizon exist, that the Big Bang happened, that dark matter is real, even though we can't directly observe these things. However, there's an opposing view, instrumentalism or empiricism, which holds that science should concern itself only with observable quantities. Theories are tools for predicting observations, not descriptions of unobservable reality. In this view, it's meaningless to ask whether regions beyond the horizon exist. We should focus only on what we can measure and predict. Unobservable entities are convenient fictions, useful for calculations, but not necessarily real. This debate becomes especially acute in discussions of the multiverse. If other universes are forever unobservable, can we claim they exist? Proponents argue yes, for the reasons above. The multiverse is a prediction of inflation and string theory, theories developed for other reasons. Critics argue, no. Without observational contact, other universes are metaphysical speculations, not scientific hypotheses. Physicist George Ellis and others have argued that the multiverse hypothesis is not falsifiable. We can't observe other universes, so we can't test whether they exist. Any observation we make is compatible with either a single universe or a multiverse, so the hypothesis makes no unique predictions. In this view, the multiverse is outside the realm of science. Defenders respond that falsifiability is not the only criterion for scientific legitimacy. Theories should also be explanatory, predictive, and coherent with other established theories. The multiverse might not be directly testable, but it explains fine-tuning, coheres with inflation and string theory, and might make indirect predictions, such as signatures of bubble collisions in the CMB. Moreover, the multiverse is, in principle, falsifiable. If we found evidence contradicting inflation, or if future theories replace string theory with something that doesn't predict multiple vacua, the multiverse hypothesis would be undermined. These debates are not merely academic. They affect how we think about the nature of reality and the limits of scientific knowledge. If we adopt strict empiricism and reject unobservable entities, we must discard much of modern cosmology. Regions beyond the horizon, the physics of black hole interiors, the early universe before recombination, the multiverse. We'd be left with a much impoverished picture of reality, limited to what telescopes can directly detect. On the other hand, if we're too liberal in accepting unobservable entities, science risks losing its empirical grounding. We could postulate arbitrarily many unobservable realms, universes, dimensions, entities without constraint. Where do we draw the line between legitimate scientific theory and unfalsifiable speculation? Most cosmologists navigate a middle path. They take seriously the predictions of well-established theories like general relativity and quantum mechanics, including predictions about unobservable regions. But they remain open to revising these theories if new evidence demands it, and they seek ways to test even seemingly untestable ideas. The search for bubble collision signatures, measurements of dark energy's evolution, tests of quantum gravity. These are attempts to probe the edges of observability and push back the boundaries of the unknowable. There's also a distinction between what is currently unobservable and what is unobservable in principle. Regions beyond our current particle horizon are presently unobservable, but as the universe ages, light from more distant regions arrives, expanding what we can see. In contrast, regions beyond the event horizon are unobservable in principle. No future observation, no matter how long we wait, can reveal them. The first type of unobservability is temporary and practical. The second is permanent and fundamental. Similarly, physics at the Planck scale is currently beyond our ability to test. We can't build particle accelerators powerful enough to probe those energies. But there's no principle forbidding such tests. It's a technological limitation. Given sufficiently advanced technology, which might never be achievable, we could test Planck-scale physics. In contrast, observing regions beyond the event horizon is forbidden by the structure of space-time itself. No technology can overcome it. This distinction matters for how we evaluate theories. Predictions about currently unobservable but in principle observable phenomena should be taken seriously but held tentatively, subject to future testing. Predictions about unobservable in principle phenomena are harder to evaluate. They may be true consequences of our theories, but they're not subject to direct verification. The edge of the universe thus represents not just a physical boundary, but an epistemological one, a boundary between what we can know and what we must infer or accept on theoretical grounds. It challenges us to think carefully about the relationship between observation, theory, and reality, and about what it means to do science at the limits of the observable. Some philosophers argue that the question, does it exist if we can't observe it, is ill-posed. Existence is not observer-dependent. Objects and regions exist or don't exist independently of whether anyone observes them. The moon exists when no one is looking at it. Galaxies beyond the horizon exist even though we can't see them. To deny this leads to a form of solipsism, the idea that only what we observe is real, which is philosophically untenable. Yet quantum mechanics complicates this picture. In quantum theory, measurement plays a fundamental role. A quantum system doesn't have definite properties until measured. It exists in a superposition of states. The act of observation causes the wave function to collapse into a definite state. Does this mean reality is observer-dependent? That objects don't have properties until we look at them? The interpretation of quantum mechanics is still debated. The Copenhagen interpretation suggests that measurement is fundamental, creating reality from possibility. The many worlds interpretation suggests all possibilities are realized in separate branches of the wave function, with no collapse. Objective collapse theories propose that wave function collapse happens spontaneously, without observers. Each interpretation has different implications for the nature of reality and observation. If reality is fundamentally quantum and observer-dependent in some sense, then the edge of the universe might be more than just a limit on what we can see. It might be a limit on what is real in a quantum sense. Regions beyond the horizon, with which we have no interaction, might not have definite properties until they come into causal contact with us, which for the event horizon is never. This is highly speculative and depends on contentious interpretations of quantum mechanics, but it illustrates how deep questions about the universe's edge intersect with fundamental questions about the nature of reality. Ultimately, the edge of the universe forces us to confront the limits of science and human knowledge. We are finite beings in an apparently infinite cosmos, with finite observational capabilities and finite conceptual tools. The universe may extend far beyond what we can ever see, governed by physics we can never directly test. We make progress by constructing theories, testing them where we can, and extending them cautiously into unobservable realms. But we must also acknowledge the provisional nature of this knowledge and remain humble about the vast unknowns that lie beyond the edge of what we can observe and understand. The Edge as Perspective, Cosmology's Lesson in Humility. The journey to the edge of the observable universe, from the sphere of 46.5 billion light-years to the cosmic horizons revealed by quantum mechanics, offers a profound lesson in perspective and humility. Cosmology has repeatedly eroded humanity's sense of centrality. Earth was once thought to be the universe's center. Then Copernicus showed it orbits the Sun, and later astronomers revealed the Sun as merely one star among billions in the Milky Way, located far from the galactic center. Hubble's discovery of other galaxies expanded this understanding further, placing our galaxy among billions with no privileged position. This pattern, known as the Copernican principle, asserts that we occupy no special location in space, a principle extended by the cosmic horizon. Every observer in the universe has their own patch of observable cosmos, shaped by the light that has reached them. Our observable universe is just one patch among infinitely many, and the edge we see is not a boundary of existence, but the limit of visibility. Recognizing this diminishes our cosmic significance, yet also liberates the imagination, revealing a universe far vaster and more diverse than our finite observations allow. Beyond our horizon lie countless galaxies, stars, planets, and possibly civilizations, hinting at a richness we may never experience directly. The limits of observation shape our understanding in ways that are both practical and philosophical. Telescopes and detectors have steadily extended our reach, yet the cosmic event horizon imposes an absolute boundary. Some galaxies will always remain forever invisible. The observable universe is not fixed, but evolves with time, so earlier and future civilizations perceive different cosmic landscapes. Scientific truths in cosmology are, in this sense, observer and epoch-dependent. The size of the observable universe is a fact about what can be seen from a particular location and time, not about the universe as a whole. While the laws of physics remain constant, the data we can collect, our access to galaxies, cosmic structures, and primordial signals, is constrained by these horizons. Unlike laboratory sciences, cosmology cannot rely on repeated, controlled experiments. It is inherently bound by what the universe allows us to see, a reality that underscores both the power and the limitations of scientific inquiry. These limits also challenge reductionist approaches. We cannot step outside the universe to view it as a whole. Instead, we infer its properties from the finite patch we inhabit. Observations of local galaxies, the cosmic microwave background, and large-scale structure must be extrapolated to unobservable regions, guided by theoretical models and assumptions like the cosmological principle that the universe is homogeneous and isotropic on large scales. While supported by observations and inflationary theory, this assumption cannot be directly verified beyond our horizon, leaving room for uncertainty. Cosmologists therefore operate with epistemological humility, recognizing that models are provisional, built on the best available data, but always subject to revision. The edge of the universe illustrates the proper scope of science. It does not claim omniscience, but provides a framework for understanding what can be known while acknowledging what cannot. At the frontier of observation, human creativity becomes indispensable. Cosmologists infer the existence of dark matter from galactic rotation curves, deduce dark energy from supernova distances, and reconstruct cosmic history from subtle fluctuations in the CMB. They design simulations, develop theoretical frameworks, and craft thought experiments to explore realms beyond direct observation. Scientific imagination is bounded by mathematics, consistency, and empirical data. Yet within these constraints, it allows humanity to grasp aspects of a universe vastly larger and older than ourselves. In confronting the limits imposed by horizons, fundamental physics, and observational reach, cosmology exemplifies the interplay of creativity and rigor, revealing not only the vastness of the cosmos, but the ingenuity required to understand it. The edge of the observable universe is therefore not only a physical frontier, but a philosophical and intellectual one, teaching humility, inspiring wonder and highlighting the uniquely human endeavor of comprehending the infinite.